Okay, testing, testing. Okay, testing. Cool. All right. All right. All right. Hello, anybody. I'm going to jump into this kind of fast. See if you got any questions here, anybody. No questions? Then here we go. So I've been going back and forth in the comments. Part of the comments, we're back to this sliding off of number 11 by the OSHA report. Back and forth with DJ and someone else. I started to write DJ, and then I said, I'll just do it this way. DJ states he's a structural engineer, etc. But in his other post, but we go on. Models are great, whether physical drawings or computer. It is not easy to explain to someone beam bending theory and how to translate to truss theory, which would then lead to the equation of equilibrium to prove 11 is being forced outward without any other of the joints at the slab shifting. Okay, so it's being forced outward without any of the joints at the slab shifting. So there's a force there, all right, is what he's saying. And you don't need movement to understand that there's a force there. To truss theory without would then lead to the equation of equilibrium to prove 11 is being forced outward. All right, so this is the slippage we're talking about. This is also the OSHA report. Let's go on. Think of the truss with simple pin connections. Remove number 12, and the canopy piece is it supports. So you remove number 12 and the canopy piece it supports. So, which I did in a video that talked about you guys. So you're removing, let's show you what he's saying here. So you're moving this in this section here. Now, and let's go back to the comment. Oops, where'd you go? Where'd you go? As they are considered zero force members here. So he's calling them zero force members. And guys, you know, I've already talked about that. I do not think they're zero force members, that they are required. They're not zero force. They are, in this design, they are structural 100%. No temporary loads like a zero force member can take sometimes, that it is required on both their parts. If you remove 12 altogether, and we're to put the post tensioning here from this guy to here, then I don't have an issue with it. But since this is 30 plus feet long, you need 12 because it's a cantilever at that point also, and the post tensioning would just would have I think theoretically would have a bending moment inside here, a flexural moment, because of the, I don't know, is it 37 feet? Quite a few people played around with the math on this, and I think it's somewhere like 37 feet from here to here. If you remove 12, would this just stay up by itself? Because it's in compression, right? And it's taut. What would happen? Would it stay flat? Would this want to flex or buckle, right? Because of the loads on it. Would it want to buckle? So how much of that, how do you stop that from wanting to buckle? Perhaps this design here is how you stop it from buckling, where it's partially at the end of the canopy on 12, it partially goes on the outside of the canopy and comes up in this capacity. Remember that on the other end of the structure, it's fully standing, sitting, or transferring loads a lot differently. This canopy is now laying on top of, I'm taking liberties here. It's resting on top of the number 1 upright. The number 1 upright, here's a joint, is resting on top of the deck, which then rests on top of, transfers loads down through the pier base, right? The deck base, this area here, and then down to the pier. This has the rods in number 2, both of them staying inside the deck. Here's the deck. If I was to do a line for you guys, And I have a image of that. So if I was to do a line for you guys, a line of drugs. Here we go. So I figured out how to do this a little more visual for you. I only figured this out a moment ago. Oh, shucks. I wanted to get back to this. Boy, it's going to take me a minute to get back to it. So you're going to have to bear with me when we get to it. But let's look at this again. Look at what we're looking at. This is the part that we see. Is this the part we see spalled off? Or is this the part that's even with the, right here, this line, is this even with the deck? I believe this is the even with the deck at this point, that we're even with the deck. And why do I say that? Because of the coloring. The coloring here seems the same. Not. So this is crack analysis, which is what we're going to come down to. Oh, incidentally, DJ, I did that video back in June, which you're talking about. There's the cut to the chase on him. I was starting to send him the link. I did a dive right here, which shows, you know, that type of load path failure. But I'm playing devil's advocate right now, and I'm going down this path. So let's look at the base of this per OSHA reports, OSHA images. Oops, blew that off. So OSHA is stating is slid off, and I think DJ is explaining how OSHA is explaining it. But I find it magical because they have it as the initial start of the bridge failure, and that's where I'm going to show you that. Well, that's just not possible. And I'll get to it. It can't be the initial problem. So as we look at this, this is the back of this guy, but there's a hickey, I call it now, a bump out that was part of the design of this structure when it was done with the decking was done first. We're looking at the decking, and then number 12 sits on top of the decking, which also sits on this little bump out that's supposed to be here somewhere. I think the bump out might be inside this guy here. These two pieces of rebar we're looking at. This one literally in here. It's on the outside of this reinforcement. And let's find that bump out so you can get a visual of it. It's going to be in the cracked images. Let me zoom out for you guys so don't hurt your eyes with that fast pace. So this is the bump out here. That's the white color I believe we're looking at. And that's the part of the decking pour. Let me give you a better image of that. As stated by the OSHA report, it said that it appears to be part of the decking pour and not part of the actual 12. See the coloration again? Not the black, but the white to this gray color, if you will. And looking at it in this point, there it is here, this bump out, if you will. Now there's the elevation. At this point, here is 12 installed on top of that bump out. Oddly though, it's not quite. It's got some elevation to it. It's not flat with the deck, as you can see clearly, or maybe you can extrapolate clearly that if this line is parallel to what we're looking here, this line appears to be even with the deck. And if so, that means when they did this diaphragm section here with this bump out, it has an edge to it, a lip to it, another unintentionally designed, not by design maybe, or maybe it is. I don't know what the plans actually look like for that, right? The working plans. But so keep track of that. Now we go back to this one. So this is where I'm theorizing this is the clean break. This would be where the sliding would have taken place, if you will, if you go down to sliding mode. The deformation I see in the rebar is here. This one's pretty mangled up. This took some that twisting action as we see in the collapse. I think this one is why you see it, the reversal in the metal. What's very important here is to note these J bars, 1 and 2. Both of these, not one, but both of them are part of the top reinforcement in the number 11. Both of them are part of the top reinforcement in number 11. Right here, this comes down, that's a J bar. Here and here, we go to the report, zooming out and chasing down to the report. I'm just giving you redundancy on my statements for you guys and tying it all in. We go to the report. There it is again. There's the J bar. This appears to show 1. Do not be confused by that one. That's still in the deck. I'll get to that. This is the J bar here. Now we have a sliding effect as told by OSHA and DJ and everyone else apparently. The sliding is coming across this decking. As it's doing that, it's pushing 12 off. And magically, they discounted both of the resistance of the post-tension bars, which are still at the inside the deck. And they discounted the shear links, if you will, because they weren't fully developed. And now ACI says you should discount them if they're not fully developed. ACI didn't address not counting other things like post-tension bar, 1 3/4 inch post-tension bar. I think that's what they are roughly. They didn't address that, and he didn't discount it. I mean, he did not give it a credit and saying, well, I'll give a credit. He gave no credit for this. He gave no credit for these post-tension bars being inside this deck, especially this one still being there. He actually discounted it because it was undeveloped. Follow that. Discounted because undeveloped. Yet, how can you count this having a sliding effect if I show you this? If you discounted all of the reinforcement because of that reinforcement discussed because of they were undeveloped. How did you calculate the sliding force, shear force of member 11 when it was also undeveloped? And you say, "Oh, I'm reaching now. I'm having a little liberty with that word now." But I can prove, you can reach for that word too. Undeveloped because of why? I like giving hints before I get to where I'm going. Why is number 11 undeveloped? Well, number 11 should be discounted too as a shear sliding force because it's trash. It's got cracks all the way in it, just like the links. It's no good. It's not actually a true member anymore. It's multiple members. Multiple members. It appears to be one member here and one member here. It's a forked member. Look at this thing. In fact, if you follow this crack pattern and you continue it up here, and it quite kind of fades here, that could be just blistering paint. But nevertheless, this appears to be cracked up to this point. If you look at this, you would say that this is failing right about here. In fact, you'd probably say, if you guys are engineers, you'd probably say it appears to be a buckling going on and a force was going in this. If I could turn this damn arrow, you would probably say it's going this way, right here somewhere, and this is where it's creating the crown, that the loads were almost on the underside pushing up. And I would probably say you could get there by well, you need some movement, right? Lateral movement, etc. You can also get there by a lateral movement that I discussed too. But looking at this only without any other knowledge of number 11 being connected to it, how many of you engineers out there would just count this as fully developed and consider it 100% engineered? I don't trust that you can now calculate exactly how much force this can apply. Who dares say you can apply? Who would dare do that? Who would do that? Would you just give me a calculation? Well, wow. And plus you said it has a sliding force. So everybody says it has a sliding force pushing off 12. This is 12 here. How is that possible that it's pushing and yet we have an opening here? Well, you'd have to then tell me the forces are redirecting, they're coming from down the bottom of this and across the top. And now they're making its way this way. So, okay, I'll go for that. But do your deductions now. But if it's coming across the top, well, how much across the top? I mean, what are we talking here? 2 inches left, and now the forces can't transfer straight down? We don't have access to this full member, apparently. We go to the bottom of this guy and look at this thing. How much of this can slide across? What do you guys get your calculations from that you can totally deduct from the stirrups that are undeveloped? But then you can add, because they're undeveloped, but then you add the full ability of number 11 with all these cracks inside of them as a sliding moment. And then you guys are just, kind of ignorant because you have cracks here and you don't know how to look at cracks and understand what's going on here. There appears to be a green dye or paint. You could get down here with a better photograph and you would see if when this was applied or not. We have an elevation marker. But if this is sliding, how do we get what appears to be an open pixelation, an opening here? Not a compressive moment here, but an opening. How do you get that? How do you get that? Well, I would say number 12 is probably got a little twist and drop, when we're looking at it, but I need more images. This was done on the 14th, photographed on the 14th. I need more. Okay. So you guys have 11 sliding. How much of a deduction did he do removing this when he did his math? Did he deduct this? Because this is a tag on, isn't it? Just a tag on to the underside of 11? Or was that added into it? This is just a chamfer. But nevertheless, it's part of the base of 11, right? At the point it's no longer part of the base of 11, how much of the deduction did he get? How much deduction for these cracks? These cracks and the removal. How much of a deduction for this? Any force being pushed down to create a sliding has to come from somewhere. But wait a minute, you guys, I'm being facetious. So the sliding force is coming from not the canopy, it's coming from the other side of this point over. Where did that sliding force come from? Well, the clamping force, right? But there is no clamping force on this at this time. This is 314, no longer a clamping force on it. As I stated in the video, this is a tension failure in the deck because the transfer load's in 10, going down 10. Clearly, that's what Denny Pate thinks also. And as the report even says, they should have recaptured in 10. But it's kind of conflicting because it also was trying to say that the sliding of 11, I think it had more of a prying action. But I think he got confused because the back of it looks like shear. And it is shear, but it's a downward force from 10, creating that shear. Because we're looking at, it's of a sliding force. As this slides off, why am I able to see an elevation difference as it's sliding out? It just bumped it over. We're now looking at the data of 314 still. It appears to be about a 3/8 of an inch rise here. And then this is even higher back here. This gap here. So if it slid it off, how come it's not falling down at this point? Well, perhaps the post-tensioning in the canopy is now creating a torque action, pulling it back up because of the design. The design has number 12 attached to the outside of the structure, not actually inside the structure. The design on top of the structure, it's like a partial of it, partial is attached to the decking, if you will, and some not. If you look at this is going to be beautiful if I can get more images of this. If we look at this, we see this crack and see what we're looking at here. Look at this reinforcement, and then look at this wedge here. It's got white paint on it. So this would go, you'd have to rotate it and put it back in place somehow, put it back in place. I don't see any of that lower bump out here, and it didn't go down for the ride. It's not there either. That's the part where people's puffer smoke, if you will. This reinforcement took the torquing action, took all the failure action there. This is where it pulled away from the deck. This is the part that's the deck number 11 and 12. The underside of this is what we need images of. There is a little box right here, a little box. That box is going to be very helpful. And the lattice work is very helpful to lining up your level here. And that's the image I kept trying to find for you guys before I could load. Incidentally, I didn't find it, but I'm sharing with you guys so you can help find the box. Hey, Mark, 11 adds rigidity by forming a triangle like a gusset. It prevents the canopy from deflecting downward. 11, okay, let's just, woohoo, I'm in for the win. Hey, Embry. So let's talk about this design real quick. Let's go back to my man. Let's make it entertaining back and forth. So someone else is, not just DJ, somebody else is trolling me in comments and trying to treat this as a truss system. It's all in compression. Linda Figg Denny Pate, beautiful system. I think that simplicity of putting everything in compression for concrete is awesome. I always tell people, how do you stop concrete from cracking on the surface when they ask me for the road traffic and all that? Simple answer, just stop deflection. Just stop deflection. Of course, know your load. You can't put a 10,000 pound, per square inch on top of 3,000 PSI concrete. So you're going to get some spalling. Right? So you're going to, that's PSI per square inch, not foot. So now stop your ground from deflecting. Stop your ground from deflecting. The post-tensioning, think of those rods, the long cables on this deck. That's the ground. That is your ground. They pull it so taut and add so many millions of pounds of force in them that's why you can get the the confidence to say, as Denny Pate said, I don't have a problem with it. Because he had the redundancy knowing that he thinks he had the redundancy, that he had the data, he load tested, and on the other side of it, in the staging area, he had it for 40 days, and he just saw nothing wrong with that. It was millions of pounds of redundancy in the tensioning, you figured, in the longitudinal cables. So when a crack appeared at the end there, including number 11, you have to realize, if you guys think about this, what I just said, if you have no deflection in your ground, I don't care if you add more weight to it. So I think Denny Pate's feeling is, you know what? I don't care that pretty much that there's a crack, that you're looking at a crack. And I know in hindsight we call him arrogant, and I went along with it too. But you got to think about that. If I'm confident that my ground has a density of, say, 10,000 PSI per inch, and you now want to apply 3,000 pounds of PSI on it, do I care? Am I worried? Not at all. I just know I got to, you got to get to 10,000. You're not even approaching my 10,000. So I don't care that you're telling me you're going to add 3,000 pounds. So you're saying, well, here's a deal. So you have a crack. He then probably calculated, well, what happens if the whole structure is now transferring the loads onto my deck? I don't care, because I still have my ground is so tight that it can hold the whole thing. Even if there's a crack there, I'm not worried about it. We'll fix it. But there's a but part to that. But that damn shimming is what throws it off. Only in that number 12 would lower down. Only in that. But remember, so think like Denny Pate and why you would have the confidence. So we're going to exonerate Denny Pate's thinking, if you will. And yeah, we don't like him because it killed people, right? And he's not coming forward. How many of you going to come forward and start going and get pounded by the press? But let's look at the images. So let's look at the images. Now, I totally think FIU is responsible in this, Florida National, because they're the zoning authority. They thought so much of it, they should have stopped it. I don't know about, they were there in the meeting. Don't pass the buck and say it's got to be the contractor to do it. What is he going to do that and then violate his contract? He's going to take it on himself. He's going to take on all the fees to stop it. He's never going to get another job ever. All you got to do is let the engineer tell you to take the engineer's lead, and you're going to be protected, you think. All right, so if you really look at just what failed on the back ass of this, would you condemn a bridge if you saw spalling like this? Well, you would not, because a lot of columns have spalling off the face of the concrete. The force, the strength is internal, not the external part of this. That's why we only need roughly 2 inches of cover to protect it from rotting. So just looking at this alone, you don't cry foul. You cry, oh, let's address this. There's some forces in there doing this, or there was something going on. But remember, the part of this that we're not seeing here, again, is that extension of this. How the hell did that extension get away, number 12, get away from this bridge? Because number 12 is acting as a cantilever because it wasn't grouted at the bottom. 12, that bump out is an entire cantilever. Do not be confused of how important grouting is. Not here, under here, we see nothing. Under 12 at this point, let's get back to it. Let me zoom out. How important to transfer the loads down. He used the other end of the structure, incidentally. How biased is that? He shows this, but we're not looking at the decking now. So Denny Pate is being toasted. They're being toasted by OSHA report here, and I guess I would be a good person to help toast. But you're showing the shear force here. This is potential line of crack between compression and tension. Compression zone, compression and tension zones. Cracks observed here before here both sides. Very symmetrical. That's nice. But look here, guys. This is that bump out that's missing. This is the rest of 12. Use this as scale of what is, if this is true to scale. We're looking at a bird's eye view, top down view, and this is D1 and D1. Top down view. This is what's sticking out. This is what's missing. This is what needed to be shimmed underneath of, because this is also what's holding 12 on. Is this guy here is holding 12 on. The importance of that is critical. Okay, so I can move away from this for a second. This we can come back to another time, but I need the damn screen share thing. I need this. I got to come down here. We need more images of this guy here, down here. We need to see more of that. So if anybody can find stuff like that, any of your channels, I'm going to snatch it up. You put it on another forum, I'm going to snatch that image up if you find it. Just again, this stuff we need clearer, so we can determine at what point this quote sliding took place. But we do have the deformation rebar. No, very importantly, this J hooks. So when this was being slid off the deck by the strength of 11, magically, it was able to slide it off without deforming these two J hooks, J bars, however you like to call them in your terminology. But as it slid off, it didn't even deflect, it didn't even bend them. So it didn't even have a bending moment inside that J bar. I find that friggin' awesome. Magic, man. You guys got magic in your calculation. I see mass hysteria with your beliefs of sliding off. This is a tension failure in the deck, and how to get there is what matters. We know what started the process. So Denny Pate is right, for 40 days and 40 nights. All right, I take a little liberty on that. It was okay in the staging area. Upon putting it over at the location, it was de-stressed or de-stressed. I'm using the words OSHA report, detensioned. And that's when crack like hell showed up. Denny Pate's argument back is it should have been grouted, and then OSHA report is saying, well, MCM said that you basically said it was okay to not grout at this point because they sent you a message, or apparently that's the way it's coming off at, as a back and forth at. Why is it so important? Back to the report. Where's my tape measure? Looking for my tape measure. So is this part of the bump out, this turn up here? This is we know it has to be in 12. Is it part of the bump out? Is that did it deform? I can't imagine the guy making this shape made this curvature, because the guys that do usually doing bending rebar are pretty damn awesome. This is going to be very interesting. I'm going to show you. I'll get to a thing on that in a moment. Where's our bump out? Let me get you to bump out with tape measure. I know we just had it. Bump out with tape measure. Where be at? So this image doesn't show the J bar there. We have one. Doesn't he? Didn't he? Right. So all you guys saying sliding out, how much of a deduction do you give me for being able to stick a straight ruler, a straight wooden ruler? We all know that. To be able to stick it in there almost 7 inches. Well, 7 inches from there, from that line there. Well, you can call it about 6 1/4, about from there. How much of a deduction did you give me for your ability to slide this off? That member's in tension, and I'm quite triggered by you idiots that say it's in compression. What this is sliding away. What stopped this from sliding off? If it's sliding away, what's stopping it from sliding off? I believe what's really stopping it from sliding off, we can talk about sliding off at this point, because yes, at this point, we do have some sliding off effect going on. But here's the thing. It stopped. What stopped it all of a sudden from sliding off? Well, because as it moved over, they loosened. They detension number 1 and A and B. I'm calling this A and that's B. And I use that because, well, they say A and B. They call it A and B. And I'm taking liberty because I don't know which one is A and which one's B. One's longer than the other. I can't tell. It's only by a matter of inches, small amount of inches, like 3 or something. I don't know. So I'm calling this A and that's B, just for you guys to figure it out. So I'm thinking what stopped it from continually falling off at this point when they had the meeting, we see the cracks. So it did creep down and they got bigger, and that's creeping down. That's the elastic ability, or possibly some more failure inside number 12 here. But it's creeping down, and why the cracks have stopped at that ability is the elastic ability of number of these guys, D1 through D6 on the other side. And what's stopping it is that when they detensioned that day, they didn't dial the whole nut off and along with the plate. The plate's in place along with the nut. And when they detension, this bar took the forces of it, cracked like hell. It then had a load. It's not just like it did take a load. Say it took a load. Let's call it 100 kips initially when it cracked like hell. And over the next few days, they didn't tighten it up yet. And so this is it's been loosened. So when it fell down and got and stopped this from going any further, it also has experienced some tension on it at this point from the forces. This is helping this stop from falling off also, along with the tensioning in the longitudinal cables. This is dialing up its forces now at this point, because it's still trying to fall off to the point where we have on one end of the structure, we have 4 inches, and it's got a torque effect to it because we have a higher section over here than the other side. Let me get the tape measure. And it's falling off and up. So here, as I showed in the video, there's 4 or 5 inches on this side. This is where number 12 is, right here on top of this. That's that huge piece right here that's missing now. It's no longer this piece of puff of smoke, gone. What kind of development did they have in there? What kind of security did they have to get this back? I don't know. This is what I think we see sheared off. I think it dropped down to this 4 or 5 inches during the failure. Bang, smashed into this. And that's the part where we're seeing this counterforce in the video at some point, where it does a weird whatever number is that it falls, it shears off, it shears off itself, falls down this 4 inches on this side, and we got about 3.5 on that side. But considering that the piers would be level, considering that, and it's about 3 1/4, we now know it's about 1 3/4 roughly, leaning. So it's got a torque effect going on, and this appears to be facing us higher than this surface here. So that means that it's tilting in, not just down, not just sliding off and going downwards, that it's actually coming back towards. So this will explain why you have your creep in the center at 10, just slightly, ever so slightly downwards. And this would give us our spalling up here, because now it's in a compression there, and it's that little, the edge lip, it's like a lip. It experienced the forces behind some of the counter-reinforced rebar. And then this will also explain why you have a tension here, opening, not compression, opening. This is sliding off. It's sliding off, using the sliding off here. It's hinging off. It's acting like a hinge. And number 11 is the pry bar. Number 11 is the pry bar, and that's what it looks like as a pry bar, to start pushing number 12 off and prying it off. Because as we look at this, if it's dipping down here, this is all, this joint is interacting at this time. Is interacting, but when they released number A and B, this being offside the deck, this no longer has a clamp force to hold itself onto there. It's in an imbalance. It's in an imbalance trying to hold itself on top of this damn deck. So I have a better thing for the damn deck, as I just said. Hold on. So I made up this little drawing here. And the purple line, I think I can grab this. Let's see. I think it will let me redo it. Let's see. Nope. Oh, nope. Can't edit it. I must have saved it. All right, so this purple line and this red line indicates the end of the deck. Correction. The two purple lines here indicate the end of the deck. And so I need to show that to you. This also indicates the path that's missing. I'm also going to state that, see where this pipe is in place? Now imagine this concrete is everywhere around here. As the forces are being clamped and all that, that concrete acts like a wedge itself, if you can visualize the shape of it. This is roughly the shape. It's got a wedge effect going on itself as it's being pulled back. The concrete not being part of the diaphragm, the decking, you're pulling back a wedge also, a shape that could also help kick out the bottom of, well, cause its own rotation failure. But I don't want to go into that too craziness right now, too much. So here's the deck, top of the deck. The top of the deck, in theory, we're looking at how OSHA says it, that the deck was done first. And looking at those, what I just showed you, how it appears that number 12 has two colors to it. So it appears that part of number 12 was also that the bars were set, that both of these bars were set, and as they were doing it, as they were pouring the deck. Now, OSHA report is biased because it's not being fair. We have a collapsed section of deck, and the OSHA report is, it's governmental, guys. And when you're biased when you come up with a conclusion that I want to burn somebody, for example, you're going to try to burn a person. Well, I'm trying to I play both sides. I told you guys, I'm neutral for data. So now I find the report, biased. I guess I'll never be in another good report again. I apologize for that, for my killing myself with that. So we look at this and look at the bottom of this, how it's going to be embedded. It's going to be embedded in concrete. It's going to be embedded in concrete at the core of the deck. He's showing the opposite end. The OSHA report is, really, didn't they have the other, couldn't he have shown the embedment of how it looked on the other end? Really, all these photographs, and we can't have a report that shows one that's not of a failure. This is not even 9 and 10 or 10 and 11 together. 9 or 10 or 10, 11. This is down the other end. This is kind of like, corrupting the mind. It's a trick. It's a trick I would use to manipulate people if I were to do this. That I won't show them that. I'll show them this and let you do your own extrapolations with everything. And with that said, let's look at D3. This is supposed to be 19, not 10. Typo error. That means somebody didn't proofread this good enough, did they? Here's your clamp coming down. Now, this is that bump out I'm referring to you as. Now it has 8-inch ID embedded drain. So at what point do I no longer count this design for transferring the loads from 12? I would, if you guys are engineers, wouldn't you sort of like say, we need to do all this connection pretty much above the pipe? Because we can't have the loads transferring around a radius. And then, imagine the math on that. Around the radius and back down the sides of this to, in the center of it, no less, to then transfer to the deck. So would you not want to, now let's attack Denny Pate's design. I've always had an issue with that. So would you not want to make that solid? I mean, couldn't you have jogged the damn pipe and came out another way before there even? I'm on the other side of the diaphragm and not even gone through this at all? Don't even go through your diaphragm. It's a load bearing number 12 is load friggin' bearing. You guys over here, my man called it zero force member. It's load bearing. Period. And it's load bearing even if you, in this capacity, if you guys don't like me, and that's what I'm going to do that to my man. So if you don't like me, I understand. It's zero force members by your thing. I trigger you on that, and I think you're an idiot for calling it non-load bearing. So DJ, I'm sorry for the attack. I totally lost it. My amygdala owned me. So number 12 is not a zero force member because it's at least doing what? Restraining number 11. As per everyone's thinking, it at least has a dead load to restrain number 11. And if not, well, we can just do without 12. It is a zero force member. It's just pretty. It's just going to hold up the pier as part of pier members. No, it is a redirect of the post-tensioning forces through via the canopy, the decorative part of the canopy. But it is critical. I can't put a piece of dynamite on number 12 and do away with it and expect I can't come at this way. Hold on. I can't leave this in place and then cut right here. I can't take a saw, cut this, and remove that. And shorten this over here. Maybe you could. But I can't do that. This is going to fall down at that point. I said that at the beginning of the video. So everyone who says this is zero force, if I cut this here, and if I cut this here, this is going to drop down. So put a saw cut in here. This drops down. What is the effect of it dropping down? You just created more tension in the entire canopy because it dropped down ever so much, 1 inch or whatever it did. So now let's drop it down. Let's drop it down 1.5 inches. 1.5 inches. I'm not extrapolating. It did drop down apparently about 1.5 inches per the images here, what I just showed you. So what kind of torque effect did that have in the canopy? If one side is down more so than the other side, it had to get one side of that down than the other side. It had to translate to the back of number 12 as you face the rear of this bridge, the back of number 12 to get one side of the deck to drop down right here where it's split. We see tape measure right here of what, 3 1/4, and over here we see 4.5 approximately. So to get this to drop down 1 inch over here, and they didn't measure it here. Incidentally, they measured here approximately, and out here they measured a tape measure over here. They didn't even stay center line with their measurements. So how biased is that with the field engineer, the BPA who took the tape measurements? If that was BPA who did it, really? You can't even do a symmetrical tape measurement to try to calculate what's going on? I find you to be lacking as an engineer. For that purposes, you're an asshole. Oh man, I couldn't help that. So then it would drop. You're dropping here. You're now creating a torque inside here. So if this was the column, this is now pushing to the right a little bit, right? And that created a torque in the canopy. In the canopies, the torque is relative. Or did it only create a torque at the joint? Did it only create a torque at this joint? So one down a little bit, and then looking at the canopy from the back end. So I'm going to have to go away from that one for a second and come back to it. So let's look at the end profile of the canopy. I think I should have gone the other direction. I think I'd have these plans memorized now, right? Nope, right here. So if that's the diaphragm. And this is just without the diaphragm. So if you were to, this is the back, you know what? I don't want to confuse you guys. I'm asking to extrapolate, and then it's, next time I get 1,000 comments about, what do you mean again? So there's a column. To drop this down, you also have to shift the column. By shifting the column, just that ever so slight bit, I think can explain, let me come out of the video, go back to the report. I think it can explain your cracking in number 11. That slight bit, that downward tape measure. So here's a tape measure here on this side, approximately whatever it is, center line of D1. Here it is over here. He's now running a tape measure on an angle, and he's over at D2. And, well, what matters is the angle from here to here. If I were to straighten that up, I might get 3 inches. But it should be over here, not there. That's actually making it look, I would say, worse. Over here is where we need the measurement. And you were right there at D1. Why couldn't you just move the tape measure over? So again, I find the guy or girl, whoever did this, to be quite a jerk with their ability to evaluate what they're looking at. So that torque that I just mentioned, I think can describe why you see a separation forward and backwards. All right, so I'm explaining why everything is happening. This crack here, these guys had stirrups wrapped around them all the way up. That I could, if this is sticking out, we could even probably determine where the torque is related to number 11, how it's receiving that torque, by which one's kicking out the furthest, which one's in the furthest on the other side. This should correlate, but I would need to see the whole thing. But it should correlate. And he did no deduction for that. So now you have a bending moment, if you will, inside. I don't know. I look bird's eye view down, a bending moment in 11. That means if you have a sliding effect, you have a redirect. So if this is no longer in plane, you have a redirect. How much did you deduct for your redirect? How many of you engineers and the other foremen and writing me here? And I really appreciate you guys writing me here. I'm not trying to run you off. I need the banter. I need the intellectual banter. So, hey, keep at it against me, please. I live for this stuff. Without it, I'd just be a lonely guy sitting behind his computer right now, crying. All right, so there's the torque right about here. Here is where, if this is dropped down a hair, an inch or so, and this is, I don't know how much just dropped down, because remember, he took a tape measure, it dropped some too. I don't know what the starting point was. He didn't show us over here what the starting point was on the pier, on this end and this end, so we can go, okay, it's level and all. He didn't do it. We don't have that data. But that torque action, right? That torque action, did it limit itself right in here somewhere? Do we have some cracks to see if it just limited here? Or did it make it up to the canopy and created a jacking effect on one side and lowering effect on the other side? And, you know, that's what we want to see. I want to see. So I said the stirrups. So I have to give you the stirrups for fairness. I'll look at your comments in a minute, but my videos just get too damn long when I go live. Here are the stirrups I'm talking about. So that torque action would have created, I think, and all of them have stirrups in them, that one crack we see, that's a crack that we see going downwards, that force could be a stirrup being twisted into being pushed out. And that's why you get your number 11, that other crack of it's sticking outwards. See, I need to account for every damn crack there is. Not okay, I can't account for this crack. I need to account for every last one. Every last one I would need to account for. And I need more photographs, more as-built, etc. That's the way I'm built. So now, here we have centerline CL. Apparently, it could be wrong. This could be a scratch. But, because it's not really an L, is it? So this is that drop down I'm telling you about. This is a huge amount that I can't quite, we don't know how much loads are on that. But we do know that the post-tensioning in this, number 11 has a rod in it. Only one. The other rod is embedded in the bed here, the decking here. The rod number B is out here. Of course, he doesn't have a photograph of it, but the pipe, it's above the pipe, the rod is. So that's way up here. So if you want to do all your fancy calculations, tell me where it is in relationship to this. And let's do that. I've been trying to find more of that, but let me show you here. So here's the pipe, and it's just below. Hold on. I think I found a better image. And so once you find a pipe, we now know what's above it. Hidden behind the concrete is B. The clamping force to hold 12 into place is B. B has a hole in it the size of the diameter of the post-tension rod duct. You now have redirect forces again once you release this clamping force. All right. How much of a deduction did you give me for that overhang? How much of a deduction? You added everything else, no deduction. So wait a minute. Right about here's the pipe. So if you guys are looking at this, we know that right about here is an 11, right? Before it turns into 12. There's a turn of it, barely turning up, barely at 90 degrees right here, right? So right here is the beginning of 12. Right there. And right here is the end of, wrong image. The end of A post-tension rod, right here. Follow this down, and right there is the very end of A. It's in the deck still, and even if it was out here, it would still be in the deck, but not over the pier. Not over the pier. I did a video talking about that could the break under here, but this is out inside 12. It's right here. Where do you see 12? Pay attention here. Sorry, guys. Talking that way to you. Where do you see 12? The bottom of 12 is aligned with almost the bottom of the deck. That puts the pipe coming through. Well, now we can triangulate where the pipe is in relationship to the deck. My mouse is not going out. So once we see the pipe, we're now going to be able to visualize how close we are to this guy getting pushed back into the diaphragm. And where you go? Back into the clamping force. Where'd you go? Where'd you go? Right, wrong one. I think it's further down. So here is the pipe. So right above this is because 6-inch radius. It says 6-inch pipe. I think they called it an 8-inch pipe, didn't they? Or did they? I don't know. Go back to it. But nevertheless, 6-inch radius, 12-inch hole. So right above this is the clamping force for that overhang, for this guy here, to hold on number 12. Anything beyond that, how much of a deduction? I want deductions, guys. You're not giving me a deduction, I'm not talking to you. Because you just told me you got a 12-inch hole between a 1-foot 9-inch pier. So you just told me you got 9 inches on each side, total of 9 inches. So we split 9. So you have on each side of this 4.5 inches. So you just did a redirect down to 4.5 inches on this. I'm saying that your loads are this clamping force and 12 is being held on by that bar, that 8-inch plate, I think it is holding this on. It is holding on the rest of number 12. Your zero force member, as a lot of you guys refer to it as. It's holding on 12. The rest of this downward is not. If you were to put the shims underneath for 12 at the back, at the very back of it, you still only have 4.5 inches on each side. I want a damn deduction, or tell me how you're calculating that you can put this radius in here and tell me it's acting like a bridge structure and it's really an arch and the arch transfers the load to the outside. I don't hear all that academic crap. Tell me how it's actually transferring the loads and then prove it to me. Do it in real testing. Make the similar thing, put it in a hydraulic press, and prove your point. I don't want to hear your calculations. If you write me on that, I'm just going to call you a clown. Don't want to hear your calculations. I don't want to hear theoretical. Arch is the strongest thing. It's going to transfer the loads to the outside. This is concrete. I would counter you with saying, well, then you're a friggin' idiot because it's an arch, but it's still concrete. So when those loads try to go to the outside, it puts the outside of that 4-inch and 4.5 inches in tension, and we're going to fail at around 500 psi. I counted you with that already. So I had your argument already, and I counted you already. So anybody write that, you bite me. Moving on. Back to this. So right here is where the 12 takes over, and the clamp, and we have some cracks here. These cracks, these cracks. That sounds like a song. These cracks, these eyes. That song has made me think of that. These eyes will never love another. These right here. That is where 12 begins. Right here. This is where the base of 11 stops. This is where everyone says that 11 went all the way, pushed 12 off the deck, or magically started pushing 12 off the deck. There's no way that 11 can push 12 off the deck without first having another failure. We have to have the other failure. We have the other failure. So you guys have to, what I'm arguing is you guys have to stop saying that 11 push, the failure is 11 push 12 off the deck. It's not the beginning. You're just telling me about one crack, basically. All right, we're talking about one, but it can't push. This can't elongate unless you get dipping here. It can't even elongate until you remove the tension from number 12 on the day of the move. It had 40 days and 40 nights, I'm calling it. It was less than that, but I like it saying 40 days and 40 nights. It had 40 days and 40 nights. Denny Pate saw it, and it only had the bracing added to it, too. So Denny Pate, everyone saw it. No one was in disagreement about detensioning it. But no one thought about how much the clamping force down here mattered. No one thought about how different, really differently these were. That this sits on the deck. That this overhangs the deck. That Denny Pate did think about shimming was required, but would that help it? I don't know. Theoretically, would it help? I would say, theoretically, I'm saying no, that it would have failed because we have 40 days and 40 nights of this clamping force holding this together. I think once you do that, you do have a solid connection, shimmed underneath, if you will. But then you still have that drain pipe that those loads have to work their way around. I could still see that. I see that drain pipe being solid all the way through this diaphragm, and this weird overhang. How much of a load of this overhang transferred? I don't know. I don't know because they, you'd have to do this theoretically this way. Doesn't work for me. It doesn't work for me because what works for me again is the load's transferring down 10. Once this starts deflecting here down 10, it creates a pulling effect because this deflects down too. So let's just get a ½ inch down here and a ½ inch here. These are tied together. So just a ½ inch drop, that creates a pushing out effect of the base of 12, and it creates a leaning in effect of the top of 12. They would move together if the post-tension rod was fully post-tension. But if the rod was released, as it was, forget that bottom. The bottom's over here. It's not even helping on 12. I don't care about this one. You can see any forces you apply here does not affect 11. Well, it does. It can cause all types of weird shit in here. It would be counter forces to buckling, but I don't want to, all right, just remove number 11 also then. The bottom, remove A, and once you remove B also, and this drops down a ½ inch, this drops down a ½ inch. You do get 12 kicking out because your reaction is 12 is coming down, 11, this is dropping down a ½ inch. This has to react. If this drops, this has to react. Once this reacts and that reacts, you think it would keep going. But again, no, these guys only loosen this nut to the point of no longer being tensioned. It re-energized, it started reworking again. That's my point. This is what's, because the Denny Pate said do not remove the post-tension rods when detensioning, that actually saved the bridge for those few days. If he'd have said remove the rods, it might have fallen right then. It cracked like hell, they said. So if he'd have said remove the rods in his plans instead of leave them there, do not detention them, do not grout them, leave them there. If he'd have said remove these, the day of the detensioning, I think it would have also failed fully, and the workers would have died that day with nobody dying in the street. I think the crack like hell was limited, stopped, controlled by this guy, this plate regrabbing, and stopping the forces from continuing down. That's all we're looking at. And then we just have creep. We just have creep over the next few days. Denny Pate then says retensioning it. that's trying to pull this back in, and this is too hollow. There's too much structural damage done to number 12 at this point, that the effect of adding all that post-tensioning and this lack of integrity of this concrete, especially what's left, this little bit of materials left, that's all it had to cause fail, and number 12 just couldn't take it. It's just nothing there. There's nothing to talk about that's there, is what I'm trying to say. There's nothing we can add structurally that's there. So, oh, right. So where are you? So remember, 11 is right here. This is part of 11. This plate, and everyone said it slid off there. So you have to tell me, when it did this sliding, how did it make its way through this post-tension bar? Oh, you just discount that too. This post-tension bar doesn't look like it's doing any plowing through the concrete here. And if it's not, that means everything trying to do this sliding is now going to have to break before it. Everything on the backside of this post-tension bar is going to have to split apart. You don't account for that at the sliding effect. Here's the edge of that. As you go through the deck, right here is the end of number A on that section. He also says sheared. This is misleading. We know it's not sheared then. It's fully in place. So why would you use the word sheared? You know, that's showing the corruption and the dumb us for washing, right? So here it is. This is 11. This is the one that's supposed to do this sliding. Perfectly okay to me. It says 8-inch drain pipe. So a 6-inch radius came with an 8-inch drain pipe. This appears to be sheared off, going that way. Okay, we don't know how much of exploratory hammering they did here. Perhaps there was more concrete on this when they did the with their exploratory at what point. We don't know, because they're not sharing that data. At one time we found all concrete to be here. Maybe the concrete was all the way out here, guys. And they did an exploratory, and we're looking at exploratory, and they're not sharing with us. He didn't share with us his process. He just gave us his conclusive file, and we're supposed to eat it. All right? And so maybe this was exploratory. We're assuming that this came off with the rest of the failure. Maybe this was exploratory. We see here the ladies on the bridge, and the guy's barely being able to pick up a couple of rocks here. It was fully rocked. He was like basically able to stand there and pick it up. Going back here, I'm just giving you food for thought. Food for thought. So where'd this chunk of beautiful concrete come from? With no reinforcement in it, incidentally. Where on the structure is there this much concrete with no reinforcement? Could that be inside 12 that fell down inside number 11 and 10, that base? And that would show that that's a weak point. That there's your easy point for failure. Remember, concrete's weak in tension. What happens when you create compression in this number B? Well, you put this internal concrete in tension. You're putting in compression. You put tension on the backside. You're also creating tension in front of it. So you're creating the tension in it also with this design, with one bar, not two, in number 12. One is being held on with one bar. All right. Where's my damn image at? So I come back to this. This shows the deck path, if you would. This shows that bump out. Bump out is here. And I chose, this is, right. So this over to here is where we see the back of number A. So this is what it would look like. This would be the sliding plane here. They're talking about where it butts up against 12. This is 12 now. So here it is butting here. It magically, they can't discount all this. They don't count all these cracks. These are representing cracks that are roughly wherever I decided. Now that means that his sliding force, he should be calculating from here, right? From this side of the crack to here is his surface plane. And if there's any cracks inside here, shouldn't he be doing some deductions? All right, but wait a minute, there is cracks inside here. So wouldn't you have, and there's cracks on the other side. I'm taking liberty putting it on this side. There's cracks on the other side that look like this. So what's the deductions for these? what are the deductions? And then we have, I chose this. Why did I do this? During the failure, I'm trying to locate the failure where the J hooks are sticking out of this, where J hooks are, etc. And this is basically, if we look at the photographs of the failure, this is how when standing on the pier, how it looks roughly. We need to account for the shape, the radius of it. So there should be two directional brakes. So rocking in one direction would crack this side, and then a redirect turning the other direction would get you cracks like this. Guys, I'm not a crack expert. I'll consider myself a crack expert when I can tell anybody looking at a pipe in the ground and somebody placing concrete around it, when I can tell them your concrete will not crack around this pipe or around this obstruction. When I can identify where all concrete will crack before placing on a flat surface. Once I can do that, I'll call myself a crack expert, and I will not be guessing when I do it. I want to get to that level of my crack knowledge, and I'm getting there. I'm working on quite a few experiments. I can make cracks happen. If I can, and I can stop. You can stop a crack, and I'm not talking about expansion. I'm not talking about quite isolation or not, because if I isolate it, I won't know if it's going to really crack or not, do I? So I'm telling you that with all my experiments, this is two directional. When we look at the, I'm going to look at your comments in a second. When we look at the breakage here, this is two directional right here. It's not one. And this, obviously, I need more. I need to know where this ends. I need more data on it. But this still has that bump out missing. That's everybody's explosive background they saw in the background. They said, I must be subconsciously blocking it. I still haven't seen it. I know it's there because it's a missing piece. But they don't count for that. And they don't count for how much of he didn't do a deduction for that landing being over the deck. If he's going to really bash Denny Pate, how come you guys don't do the deduction for the overhang that you really only need to slide off this much? And then doing that, how come you don't add back in the clamp force of B? As you have it sliding off, this clamp force is hit and it's countered. How come you guys don't add that clamp force back into there? This nut was loose. You now have to tell me about the elongation, how much sideways, the force coming at it sideways, how would this resist? I want the math. Or don't discount it is what I'm saying. And you can't give me the math. You can't make it up. You just don't know. But you now see that it doesn't work. I need more photographs. I need more of this to know how this interacted, this trumpet area of the post-tensioning through here. How did it interact during that crack down there? So they took photographs, that engineer. Or did he take photographs up here? I would love to see him take photographs up there. Did it crack right there? If it's cracked, now we're sitting on top of a precarious column, right? It's just sitting there. Let's add back the effect of Denny Pate's orders of post-tensioning. So they do this one. It's reportedly 50-50-50. I just need to know that crane operator told me he moved that thing 11 cycles. It's provable with the crane operator. And also those photographs they did of the damn bridge back in the time lapse. Let me look at two notes I wrote down here for you guys. I said load testing, right? And I said under development does not count for non-element, right? I already said that. So Denny Pate adds this back. I think that the broken concrete in here, it no longer had the integrity to act like a clamp anymore. And so basically, 300,000 pounds of force just caused it, just broke right through there. Just look whatever's left. And we only have this wedge here. See the shape of this before we're back at the deck? Before we're back at the deck. So I'll do. So there it is. How much of this? Get out of the way, thumbnail. Um, so right about here is the post tension bar. Right there. Not down here. It didn't go through the pipe. Only here. So you count all this as pretty much just a stump, a damn column to hold up the rest of this. It's overhanging. Why did they have the feeling? Why did they have the intent that they needed a clamp outside here? Why not clamp 12 inside here? Why not clamp 12 inside here? Because you could not. Because 12 is part of the upright installation of the deck, of building the deck. And so they need they want a clamp force to hold 12 onto this structure. Because all the other clamp forces, adding all the other clamp forces. So remember I said the system where they were clamping clamp number 2 and clamp number 1, then come back and post tension these. I'm sorry, when I say clamp, but post tension them, tensioning. So when you loosened 11, there is no, possibly there were forces coming down 11, right here, down 11. How do I say possibly? Well, because you're creating that force with Linda Figg saying this awesome design, it has compressive forces. If it has compressive forces, it also has a sliding force, right? In this case, yes, we got to redirect. So, but it didn't start that way because you had to start this failure, you had the first loosening up, the detensioning, starting the failure. And now, so here's 11. I have it wrong. It should have come all the way down inside the diaphragm here. No, it was before. It stops before 12. So this is right. So this is inside here, but down here somewhere, in line with right below D1, in line with below and above the pipe. Huh? The other one's above the pipe too, right? So you see how those forces are going to triangulate against each other with the bit of concrete that's above it. The concrete, I think that there's a wedge to help make this fail. Let's go to back to that. Right. So here is the pipe. So this stops right there. Here's a pipe coming through here, and here's it right along the pipe. So they're in level and playing with each other, as I stated, going across there. That you detension. Where's my detention at? Oh, it was in the same damn image. Now it's in the drawings I was looking at. Sorry. So I don't know what pattern they detension A and B in. All right, I wanted to use the picture. I want to use the darn picture I had. Can't believe I lost the picture. Danielle, hold on. If I read, I'm gonna get so distracted from what I'm trying to say. So you guys hold on. How's my picture? That's what happens when your brains don't crack. So right there is where it stops. Right. So detention A and B, detensioning the day of the failure. They detention, as I said, if Denny Pate said remove it, this damn thing would have been on the ground. Failure wouldn't have been no creep. It would have finished itself off. And that's because he didn't figure out that 11B had that much capacity to keep 12 on the deck. That it was part of keeping everything in compression. That number 11 was so critical because of the way this design came out. That this diaphragm is just wrong. That's the failure. The diaphragm is wrong. I theorize it could 100% work if they did the same type of setup down as they did down the other end of the bridge, down 1 and 2. But because they released the clamp force here, because they did it on the other side also, this guy had nothing to hold it from the forces now, from detensioning, to start the evolution. That the force is just, especially detensioning here, started the shear failure, the torque action, everything. Detensioning was again the beginning process. That caused that break. That then caused the redirect of forces down 10, and trying to resolve itself by regrabbing itself in all these D1 through D6, and a little bit of the canopy also trying to keep straight. The canopy is deflecting, having just a half-inch. I'm just calling it a half-inch deflection. Can't move this. All causing the issues. I'm just looking at it. Her thing was beautiful, but the moment, okay, that's where I'm driving at for you guys. That it's not. I'm sorry. So once you detension this, it actually became intention. Let's keep my story right. It became intention, not the sliding effect. It became intention, and all the forces going down 10 again because the cracks show tension breaks, not compressive breaks. That at one point, once it loaded down, yes, it stopped it. Yeah, it stopped it right then. If you'd have left it alone, it would have creeped. It would have creeped and creeped, and ultimately they would have condemned it, I bet. But once you came back to tension it, that's when you cause this other force to come in here with this raggedy, non-structural ability. When you try to do that, it made all this fail. That big hunk of concrete we see on the ground, I wouldn't be surprised if it's right inside here between all of these members, between that it came out inside here. Well, perhaps that's this piece here we're looking at. I'd love to see more of that hunk, but it's in here. So our failure, if we follow this pipe plane and try to, the pipe is level pretty much. So follow the plane of the pipe in here. I want this damn image again. I don't think it'll let me load it as far as edit it. So I'm going to be able to do this. I'm just going to write on top of it. So bear with me on this. So I do markup. I'm in markup now. Okay. I want to use this crazy. I want a freehand pencil. So this is level. Now, not with that one. I want to do. I'm going to take some liberty with my ability to level. I'm going to do the front of the pipe, and I'm going to try to extrapolate a little bit. So this is photography too, so I need to figure this out. All right, so my vanishing lines are in this direction. Trying to match these vanishing lines to give you the same plane. Whatever. So I know I did that, but this is for you guys. I'm trying to line these lines up. This is sort of the plane. I'm trying to match this stuff up a little bit. If you could imagine, I'm really doing a line down the end of that deck down to there. I just can't do this. That's not quite fair, but I think I might. Yeah, that is the vanishing, more so the vanishing line. Right about, oh shit. I'm taking liberty on that. And let me do this. Oh, I'm going to go big. That's the pipe. Can I go any bigger than that? Apparently not. Oh, I can do that instead. I'll give it a chatter mark. So the chatter mark is the top of the, so that's chatter mark is the top of, we're going to do the intersecting of what's left. So our plate is here. So I grab a little square. So our plate is here above the pipe. And that's roughly where that black line is. So let me get out of that. Come over here. Really? It's going to keep those things on it? Oh, you jerk. So that's our plate. And what's left is this little bit here. Let me see something here. That's our low path. That's our plate. This already dropped down. It's already deteriorated itself. You try to push it back. That was just madness right there at that point. Because you can imagine if you try to push it back, or even your only clamping force is what I'm trying to show you guys. Okay, I know what to do better. Your only clamping force is right here. This is better. Right above the pipe and right to there, because the deck is here at this point. Internally, you've got these cracks we see here. Freehand. Oh, hell. It is edible. Delete. No, let me put that back. I just want to move that away. Delete. Delete. So here's our clamp force. And if you're applying a clamp force to this 12, it's not going, it's got some, it's going inside the deck there a bit, right? And this is what I'm talking about, where it would work against you to have, and there's the other bar internally here. And I started to do a diagram of that. And let me see where I'm going with this. Let's go to here. So I have that it's outside of this plane here. Here's the plane, this finished surface. Remember, it's out there by that bump out. It's out in front of me here in a square, if you will. But it's above this pipe. And you only got what's above that pipe is only what we know to be, what is this, 8 inches, and that's maybe 10 inches, maybe 12 before you get to the top of this pipe. So between the top of this pipe and the top of the beginning of the deck, that's what's the clamp force to pull 12 back in. But remember, 12 already look like crap, and you can't really put cracks back together. You can take them apart, but you're not putting cracks back together. I don't care if I've attempted that incidentally. They don't work. They create debris inside there. They just don't go back together. So whatever debris is in there, you're now clamping against that debris, and that's where you're getting your false readings and things like that. And you're creating tension in the backside of the member. It's drama. It's gonna happen. I never heard of attempting to clamp back a broken seam like that, a broken joint. So that's where Denny Pate gets the loser award. Come on, let me have my free hand. I think I have to choose it. Let's see, go like this. Right, squiggly, give me free hand. Jerk. Bear with me. Free hand, I said. Free hand. What the hell? Oh, I'm live with you guys too, and this stuff has a tendency to software had a tendency not to like all that memory being used, and I get all types of weird stuff. Yeah, whatever. It's controlling me now. It's owning me. So we just got cracks there, cracks here. Now this helps you visually. Instead of a bunch of little teeny pictures. Really? Wow. Come on, play nice. Got some beautiful symmetry going on as you see we draw the cracks in, right? So we start getting some symmetry. And you can see where you lose symmetry with cracks. So on the other side, I can't draw it on this side because I don't know, but it goes something like this. Something like that. At the deck, we have a breaking of, I'm taking liberty on each side, right? But you guys are getting the gist of it. Right, that's being me. Right, let me draw it then, didn't it? I think it overlaps. When it overlaps this, it goes to the hand, and I don't want a hand. It can't tell I want to overlap my crack, so it won't let me do it. Just trying to think if I give it a larger view, but let me do it. So I'm just taking liberties and put it down here now. Might be pretty damn close though. So that's the crack at the base, and then we have crack here. We've got multiple cracks on this. It won't let me have at it, so I'm going to just do this. And what do you notice about the cracks below the pipe? What do the cracks above the pipe tell you? They're on the side. Doesn't appear, it might be a couple of them on the back or not, but you start adding all these cracks up on a drawing like this. Much better than this. But you start adding them all up and you draw them out, and then you account for every single damn crack. Tell the story of how they started. Tell the story of what did all this. You know, figuring out forces and everything else. How would you get a crack down here? If this is connected to here, could you get a crack there that looks like that? And you would know the opening. You saw on this side, I would say plus +1/4 inch. Down here, I'd say, 1/2 millimeter. Up here, this one I would measure going up. This would say 1/2 inch. This one's just say quarter inch. And you see measuring the front and end, it tells me where they started, the front and back end, how they started. But you would measure the width of every last one of them, the length, map it out. And all of them would tell me what's going on. They would all, but every last one would be accounted for. There is not one crack that wouldn't count for. It's a crack up here. Obviously, there's a crack up here. There's a seam here. So there is no post-tensioning going through here, apparently, right? As we look, it's just out here. So what's holding this together? What's holding this joint here together? So this gets its own little joint. What's the width here? All right, let's look at your comments. Let's look at your comments. You're getting the idea now what's going on here. So the brake, though, so let me get rid of this guy. That was a clamp. You guys got it. Let's put the brake in here. This is a natural brake. Right, come on. Oh, right, I'll do another one. So that's where it was jointed. And then this has a crossover to this point here. So what do you guys notice? That this cold joint, that's the shear they talk about, but this also has the cross point here. So all you need is a little dip here to start getting this thing to move over. But what happened when it moved over? I'm going to end the video, my comments with this, because this is the part that I ultimately all got to the end to show you. What happens when you start sliding this off? You're like, yeah, Kai, it slides off. You just said that these are separate. I did. So if it's sliding off, how are you getting all this shear vent down here, down the outside of this diaphragm, going like this, here, here, and here, and here? If you just told me it was pushing off 12, I agree. But I told you a different way of pushing off 12. This is why I'm saying the loads, when it released the clamping force, 12 is not a zero force member. It has a downward force. And that's how I can explain the shear look we're looking at. The downward force of that is greater. The redirect is greater than the sliding, if you will. The sliding, you can only get a bump, a slight, when this drops a ½ inch, you can only get a little bit of bump there, but you got to remember these cracks. You're going to have to tell me how you got a sliding with all these cracks in this member that are open, which is a tension break. It's open, not compressive. And I know most of you engineers out there don't understand that because, well, you're not a crack freak like I am. It's open, it's tension. That means it's not compressive. You can't push somebody down with an open arm. So this is open. So this deflection here and this dip down, this is the counter force, all 12, no longer having the clamp force to keep this all in compression. This is the tension break here of number 12 pushing downwards on the outside of this diaphragm. That's that. Because again, if this is 2 pores, which we see it is, apparently reported by OSHA also, this is on top, that would just slide it off. That would slide off. Now, you could argue that, well, no, it would create as this slides forward, it creates a, looks like this. Oh, great. It looks like this back here. Okay, so how much did it move to do that? Tell me how much. I need to see it. This is during a failure. It did some action like that, but not with this. But let's the tension. Let's just look at it and what tension looks like. Well, that creates compression on this face here, tension on the back side of this. Give me my deductions for the reinforcement in there. Tell me how much, but there's reinforcement going up here. We see it standing proud. You better give me my deductions. You know, what's my deductions for that before you just told me it can do that? And if it did that, what did you just told me is this would actually make this lower, closer to the top of the pier, not further away. Not further away, and you have to have a break. But you also told me that that this is so powerful. The concrete, the rebar reinforcement is so powerful, developed inside here, that's how it's able to cause a shear event down here like this. You can't have your cake and eat it too. You told me to discount all the shear ability in here, but yet you just told me how concrete created a shear crack all the way down here, all the way down here from the forces of the sliding event here. A sliding event off of here created a redirect of shear event down here. Again, the sliding event. So let's change the path of the shear event. I mean, of it. So here's a sliding. So that's only pushing 12 off. Where's the extra force come from? You just told me it's a zero force member. During the crack, during the failure, you can get this to happen. But we have it way before the failure. This is before post-tensioning happened again. Before retensioning happened again, we're looking at these cracks. So everyone who's looking at it is telling me that this slid that little bit and then created a redirect. No longer it was able to redirect the forces to come down. Remember, it's number 11, the bottom of 11 stops right about there. We only got about 9 inches. 9 inches of force left in that column to do any pushing against this guy. Because you have to go through the upright. Through the base of 12, the base of 11. Now, you want to explain? I'll explain to you this little crack to help you guys sort of troll me back, if you will. But that's not. You don't have this. My full lesson is not handed to you. It's got more to go. This is only you don't even like my virgin class of cracks. Here's the bar coming through the deck. The bar is coming through the deck, and the image is presented here beautifully so by OSHA. I'm going to let me explain this first. Let me tell you what I'm going to explain, and then you'll have the oh shit moment too on that. But don't get too carried away and think you understand everything about cracks and jump to the conclusions. That you're wrong. It's not supporting you in that capacity. Let's go here. It's supporting its dipping in 10 and 9 and 10 is what it really supports. Come on, really? Did I just blow past it again? You got to bear with me. I'm going to show you how something happened here. I'm going to explain another crack just so you guys can see how I see all this. All right, so this crack here how did this crack happen? What is it talking about? He only took 1 point, a half inch here, and not the rest. What's going on here in this crack? This appears to be right underneath of 11. You guys, if you're graduates of my class already, you would know what this is. I gave you the hint already. This crack is from here. That post-tension rod that's it goes up at the bottom, this is A, has about 2 inches of cover, as we see, as we know. But at the bottom, there is a chamfer, or 8-inch chamfer. And as the deck is creeped down in the middle just a little bit, the forces of that resolve itself against the backside of this rod, and it presents itself as that crack. This thing was, if only I had access to this bridge when this is going on, I would have seen all of this. I mean, it only took me 1 day once I seen these OSHA pictures to put the rest of these crack story together, to see it. And it's taken all these days to talk to you about it, you know, as far as adding to it and everything. It's just forever long. Each one is in my waking moment. Each one is in my waking moment. So that's that one. Remember now, there's also a rod in here coming down 2 inches, come down 2 inches, and we slide down going into a clamp force. I don't know. This is 310. This is the day of the release. This is the beginning of this thing creeping down, between 10 and 9 and 10 creeping down. And it's now the underside of 11, and inside the ductwork is now feeling the forces in that rod. The rod is taking on a deflective moment now, a resistive moment. It's a torquing moment at the canopy, because you now imagine the center of the force is going against that rod now. It's got an action going on, but internally, that creeping is also resolving itself in that 8-inch plate that's back here. I think it's 8-inch in the back of B, trying to push reclamp 12 back on by default, automatically, and by default, because it's got to fail too. And over the next few days, that rod experiences elongation just by the forces on it. Before Denny Pate even said retensioning it, I would love to know what it started at 0 point, at what they call, you know, the starting point. It was not loose anymore. When they came up there to do that rod, I would love to hear one of them tell me that it was hand tight. It was just hand tight. That would be awesome to hear. I would also look for a pinch point at that point inside the rod. But I don't have the rest of the photographs to determine that. Because we know if this deflect, what's going on right now, if the rod is 1 3/4 and a duct is so much, our ducts have failed. They now have cracks in them. You got to give me some deductions for these cracks. How are you able to move this much and you have no failed ducts? All right, I'm going to look at your comments, because this can go on forever for me, believe it or not. I just love cracks. I love cracks. It's not troublesome to me, but it's troublesome to try to explain it. Oh, Danielle, that's what I'm talking about. Look at that confidence. 11's only moving because the forces are redirected after detensioning. And that changed this whole compressive moment, this whole compressive system. It changed it. It redirected down 10. And Denny Pate was right to be kind of cocky, because I swear that I think it would work too, except for, remember, I've always beat up that, wow, I always thought it would be like a punch and shear, an issue with the load distribution across D1 to D2, D3. And that's how I see the failure, that it was always an issue at D1, the center line, and that those forces ultimately could cause ultimate failure. But back up. Let me back up my statement there. Is that, remember, at 40 days and 40 nights with number 2 and 11 tensioned. So and the bridge didn't fall to the ground. And with the bracing also. So I may say that, but I have to retract I have to say on time, and that it would have failed in time. Well, that would be 100% true, right? Everything fails in time. But I'm trying to say that it would have failed because of result. Even if you left 2 and 11 in place, I theorize that the longitudinal cables would have overloaded themselves in due order, especially D1s. Also, that the deck, the center line of the deck, would have really, it might have failed my guess when they put those 16-inch ductworks on them. That I could see that happening. Okay, I don't see VSL coming forward bragging about the post-tensioning abilities, about how they double check, triple check, whatever. You know, when I do something and we have a banter like this, you see me going at it, and I'm willing to change my position. But this is how I am in real life too. I'll fight right out in the public. There is nothing, I don't need to hide. There's no reason to make a settlement. We can fight about it. And, you know, if someone wants to, you can't beat me. You can't beat me because I'm not going to make the mistake. I'm gonna have had the question answered and asked and answered. It's not going to be a mistake. And if I do find a mistake, so someone I have in part of my motto is it says a professional, right? That people talk about, a professional knows how to hide his mistakes. A lot of people said that. No, a professional recognizes mistakes and knows how to fix them. That's a professional for you. An amateur is the one that keeps hiding his mistake, hiding behind it. Oh, let's cover this, let's do that. Now, a professional will also say, this is what we need to fix it. And somebody then says, we don't have the budget for it. A professional will document the hell out of that and then keep on going forward, going, hey, it's on you now. And that's the size of that. Mark, 11 had nothing to slide to, right. So it can't slide on this, 11 can't slide on its own without a failure mechanism before it. That's my final 100%. Eat me, bite me. I'll bet $1,000 that 11 can't slide by itself without detensioning first. And I'll base it on 40 days, in fact. But I'll base it on it can't elongate without removing tension from 2 and 11. 11 can't move. Let's finish off DJ here. Now the lower truss keeps its level. This is what I described in my video. So he's just describing my video from June, right? I was giving him a link and I decided to do a video. DJ, I did a video back in June 2018 on this tension failure in the longitudinal cables. Now, how we got there, that is the question. The overloading of the longitudinal cables is what is the issue at hand. This is what the issue at hand is. My response to him was that, wow, that detensioning was called for. How did we get overloading of the cables? Again, I think it's because a 12 was being clamped on by one bar. It's not, if the whole diaphragm, meaning the pier was put in place, the backspan was there, 12 couldn't push away. So what's the issue here is that if they got your program, run your computer programs, and don't run it with the entire bridge put together, run it with just this standing by itself. And now run 12 and removing 11 and 10. And let's see what happens. Post tension 2 and 11. I want to see that video run. And now we'll see that, oh, wow, you don't have the backspan to hold 12 in together. You don't have that development of all the concrete to hold the two of them together. So, yeah, 12 is taking up force at the ass end of it, pushing out once you detension 2 and 11. Also, that dead load spin. Okay. Yeah, right. I know. With all the new photos, this is insane. They didn't close the road. When I watched your video the other day with the new photos, I said to myself, WTF, the compression force zone 11 was not uniform through its cross section. There was a force gradient with a, marquee. I wish I had all the photos together in a panoramic. What's up, brother? Hey, Blonde. What's up, Blonde Bindi? Their math is 1 + 1 + 1 equals the bridge fell down to kill people. You're saying you're on crack. Yeah, crack, man. It's my brain on crack. Oh, man, show Embry. Virgin, he says. Virgin, huh? Kai is a crackhead, a crack addict, crackhead. I'm a crackhead. I wonder if I get a video that says that. Yeah. Well, I troll myself then, like I do a counter argument and then troll myself. Yeah, Embry, but I gotta but then what did I just do, man? I just attacked the report, didn't I? So I'll never get mentioned positively again. was that positive to begin with? Finally, I think you said that the cross-section stress distribution on the longitudinal cables was not uniform. In my opinion, that might have been the fatal flaw. It's not. You know, when they were back and forth, it was just, you can't just put crack concrete back. He figured out what happened to make the bridge fail. I think that was what he has shown explains it. All right, I forgot that. Yeah. So, yep. So there you go. They have it going, this lateral sliding across the deck, separating. They removed the bars. They removed everything, and magically they just have it's sliding. But they're not talking about, most importantly, that detensioning took place first. Forces got redirected at that point. They're just trying to blame undeveloped. They're trying to blame engineering. You can blame engineering still, but why blame it on his joints? I told you guys that we can talk about those joints till we're blue in the face, but I think Denny Pate is awesome with this. If he's the engineer behind, if he is the engineer behind the development of the joints. Where's the slow motion death? What, really? What do I do with the main video? Google something else. They dropped it way down here now. One of the main videos. No. So in this case, the owner of this image video, it belongs to the driver who apparently put it out for the public to have. Anybody else sharing this on YouTube does not own it. So they cannot claim copyright, just so you know. The owner is the copyright guy. You're just sharing at that point. You're not the owner. You can't claim copyright because you shared it. I'm almost done. Yeah, I just want to show something here. So this is how badass Denny Pate's engineering is. Everybody's talking about that he didn't have enough development under his shear, under his joint out here. Well, I can find that to be a false statement in this start part. That if that's the case, that means his engineering sucks with all these other joints. If you're so badass to figure it out, everybody's so brilliant now to see collapse here, and all of them say it's shear failure. They're undeveloped this and that, and that's why. Well, pick on this one then. Pick on number 10 and number 9, 10. Have at it. Have it 9, 10, because this is the one that experienced the most force. And yet these clowns, these engineers out here who I find lacking with their inept, disgusting abilities, can't pick on number 9 and 10. That they don't understand why they should even be considering picking on 9 and 10. You should pick on 9 and 10 because 9 and 10 had the most loads. 9 and 10 and the canopy, the node 11 and 10 had the most loads. Now, if you believe this is a truss system, it may have acted one during failure with the one pushing out ultimately. But if you believe this is a truss system, well, then you're in crack. You're on crack now because you're joining me on the crack. As you're on crack, you've got the real crack perhaps, because Linda Figg and Denny Pate came up with this awesome compressive system, never putting the concrete in tension. Awesome, not never, but not putting the concrete in tension. This is 9 and 10. It looks pretty similar to this. You know, of course, this is wrong out here. There's development out there. But as you look at this, how come you can't make 9 and 10 fail? Because it has the entire load of the bridge all the way down to here. It does not fail. The crack happens back here. So if anything was going to fail, all the loads is bending here. How come it doesn't fail here, or here, or here, or here, or in shear here? How come it doesn't fail? Because his engineering is badass there. It nailed it. Where he missed it was he detentioned, whatever reason. Maybe the grout would have saved it, maybe not. But the grout was critical to this system. Also, this is a totally different end. Don't forget that. I did a video on that. This stands on top. This is outside of it, you know, blah, blah, blah. We already went down that road. This is badass. His development, you relax, you shoot at it. And I say that you can't shoot at this man's engineering. You can shoot at he dropped the ball on one thing, you know, and MCM and also FIU dropped the ball. They allowed it to happen too. This is flat. There's no deflection here. There's no shear failure inside this member where it's got the majority of the forces. And I figured out this the other day. This is because this doesn't have a banner on it, and this one doesn't have a banner on it while we see ghosting. Yeah, in photography, it's a computer processor, a sensor in there. It's not really as magical as you may think. It sees, you know, it relates everything over to numbers, right? And there's these shades and pixels. They're light, L-I-G-H-T. And it sees the light on the blue stood out more so than this light, this color here. It was too non-contrasting. And this is the best it could do for processing. It's a dash cam video. What do you expect? So that's not magic going on here. So now this is already, I don't know if this is already broken here. It's got a weird thing going on, doesn't it? It's got a weird thing going on there on that one. But here's the top of the canopy taking a revolution in that direction. It's going to revolve back. It's going to take a revolution back at us. This appears to be going down this time. This is supposed to have this sliding action going on. I don't see a sliding action. If this is still in place, it's still not pushing off. Even during failure, I don't see it sliding it off. Wasn't it already doing that as they intended? But I see where all those cracks were told that were reported. I can see it now, disintegrating gone. It had no ability to hold on. And apparently 12 didn't slide off because 12, this top of this canopy, guys, is standing proud as fuck. It's standing proud. Google won't censor me. You heard one curse word. This is standing proud. It's still taking load standing up. In fact, it's kicked a little bit. Possibly this is that blowout that everybody's talking about, of the back of that nodule, that part I told you about. It might even be sliding back on the deck at this point, clearing out. So it's a redirect, right? Right now, it might be clearing out that hole, routing this hole. So it's routing this hole, pushing 11 more so out of the way. That's redirect. So I'm going to show you with that other image. So a redirect, and I want to get the sort of top image of it. So as the number 12 now is pushing inbound, the base of 12 is pushing inbound towards this bar here, towards here. Not even dropping down and breaking his pipe, but it's still just redirecting, turning towards the base of the 12 has a inward motion. At that point, the back end just peels off. It was already done anyway, as we know with the cracks, right? So that's an easy fail on that one. And I want to get to the top. So right here, one on better top than that one. I think they'd have it at the bridge failure. Yeah, so here's the bridge one. So at this point, number 12 is kicking in, turning inwards. At that point, we can explain some of this breakage here. Not that it slid off and this is a downward thing, but possibly upwards. Take note of this piece of rebar here sticking out, this little knot, this little nothing. I didn't want to give you that one yet, the little knot. I have another image of that, and it's talking. I was going to talk about it. These are your pipes right here. You now see when this finally went through. This is if they did not do anything. This is our path. Look at these guys. We have a path, and we have uniformity of a path of the failure. These bars here. If you can locate these bars and how much they crossed each other, you see the path now. And you also see, what do you see now? We know and here it is again. And there's a uniformly come across. Where's my little nodule I told you about? Let's go back to the path. So we have the breakage. We have it turning in, coming in, kicking in there, destroying the base of 11. 11's just, nice move off. But remember, 11 still has the bar at the bottom of it. Number 8 still connected. This was an easy sail as far as destroying it. This is going to come down. It's going to do a redirect. So it's going to be a pixel camera not following thing, I think, because it doesn't compress this much. Or does it? So this appears that maybe, let's just try that. So here's the base of 12 at this point. But here up here is the pier, I think. It's going to take a bump. Here's the final, almost the bottom hitting. We're still in the air. In the air. 11 appears to be like totally compressed here, flat underneath here. And now this will be 12, I believe. This is still standing proud. Number 9 is standing proud. Not fully, but it's going to start compressing. But back to here. This is the top of the pier, I believe, right here. The deck just took a bounce, pulled off because the cables are still in it. Pulled off, the cables are still connected, D1 through D6. And this still has a pulling effect to it, a jerking to the side, lateral effect. 12 is going to come around, 11 is going to stay in the air, right? Right here, I always found this interesting that it's going to take another bump. Or right here somewhere, you're going to see it take a bump. Okay. So much for that. This guy loaded up a video that sucks. You could normally see the extra bump. All right, comments. Finally, I think you said the cross-section stress distribution on longitudinal cables was not uniform. Right, Mark, thanks for reminding me. Yeah, they seem lacking to me, that they were like 260 kips. For this structure to have all those 4, but I'd want to see a punching thing, but maybe it did. We don't know. But, and I don't want to, they didn't show us, but I'd like to say there were some cracks. Well, we know there's a cracks where it failed. I'd like to say, I did a video on that, right? Talking about the nodal area, the transfer of the loads didn't break between 10 and 12, but broke where it did because it was more like a flexural shear point using the bottom nodal area of 10 and 9 to be the transfer of the most forces trying to make it out to 12. Wow, that was some crazy talk, right? So what I'm saying is that when it was down here, there's a nodal, right? The way it's encompassed. Oh, this 9, 10. This has a nodal area. As 10 comes down, this has where forces would coming down there, where we see the break. And so memorize this. Here's a drain here. That'd be a nice weak point, wouldn't it? So sort of memorize that nodal area of the deck. So it's super reinforced there, so much so that you saw how the bridge broke. It didn't fail. It said, I'm not failing here. You got to find another weaker point. And that weaker point has to be between me and the pier. And it could have been shear in the pier, but no. If it was shear in the pier, then we know the deck was really badass and it was just weak and shear at the pier. But it was not weak and shear at the pier to that type of load transfer. It was, okay. Oh. Okay, we'll just use this one. I said nodal area down 10. So the forces are here, as we know with the failure, obviously. And so they make it out to here. So you would think that the weakest point between the unsupported span is here and also in shear. So it would be between here or shear, however the strength of this develops. Ooh, shit. Am I ready to change the reposition? I just might. So this is a flexural break right here. Is it a shear break? Break right here. The loads are here. Yes, it's going out to here. I know it's on the other side. Can I call it a shear break? I'm saying the loads are out here. Okay, so don't imagine a dead load of the whole bridge. Just imagine a load being with an arrow right here. This is a load coming down right here at this joint. Applied load there. Could I actually call this a shear break and not a flexural break first? I said flexural. Could I call that failing in shear? I'll leave that open for you guys to work on that too in your brains. I'm now considering that could have been a shear instead of flexural. Flexural would mean that, again, the cables didn't hold it taut enough, and the loads are down here. It is a cable we're talking about, though. The cables would have to elongate. I don't know if you can call cables shear break. My brain is overloading now. I don't know if you can call cables a shear break. The deflection here. So I don't know if you can, but I'm gonna call it flexural now. Reserve the thought to work on shear. Yeah, I'm not gonna sleep now. All right, so the loads came down here because they would no longer come down here. We know that again because these are tension. It's not going down here anymore. So the Denny Pate's construction engineering fails in the capacity that why would he assume this would be in compression if he removed it? Because as my man says here, DJ, so I'm going back to give DJ, not DJ, actually another guy trolling me. So I am now going to give him, oh, he's probably going to come, he's probably so excited. I'd love to give him a little props. I'm going to give everybody who says this bridge, I'm going to give you all props, who says this bridge acted as a truss member or as a regular truss member, steel bridge, if you will. Linda Figg says everything's supposed to be in compression. My statement is that though this is no longer in compression, this is in tension and the forces went down here. Let's add to the fact now that they added a 12-foot extension onto this bridge approximately. People ask, could that cause the failure? Now we probably can. If Denny Pate and Berger had an assumption that their first drawing worked, and then they did the 12-foot extension, and they forgot about that 12-foot, the load. Well, no, they used this computer program. So their computer program backed up what they programmed it to say. Interesting. This is why you can get a pair of scissors between here because it's in tension. The loads are going back down here. They're redirecting down here. It's put this in tension. That's why, again, you saw the cracks in the format they're in, pulling back, that this thing was in tension when they loosened it, and that day it cracked like hell. That this is the only one, 2 and 11 were the only ones that they released the loads on. So Linda Figg, Denny Pate, they violated their own rule of keeping the bridge in compression when they detensioned. So there's the engineering fail right there with Denny Pate and Linda Figg, that they violated their own rule. But why? Why did they violate it? Because they assumed that this was going to stay in compression, just like they assumed this one was in compression. See, no members in it. And they assumed this was in compression. I mean, how much money would it have been to just add more cross member in this? But they were right. This wasn't compression. How do I know that? How the hell can I say that was in compression? This is why I can say it. When the bridge was failing, if one was failing, if this was not in compression, we'd only have compression here and compression here. This was compression here too. Would this not have separated? It went along with it, but that is pixelating, so oops. It was in compression, and there's nothing going past each other. So they assumed this would stay in compression. They didn't need it anymore. It was only for transportation. If you guys remember the 2016 plans, which I no longer can find, that we all got suckered on working on them forever, and then they updated and put 2016, 2017 together. They merged them with this new drawing. They added post-tensioning in number 11. We all remember there was no post-tensioning in number 11. Do you guys remember that? There was no post-tension in number 11. Imagine if Berger didn't verify Denny Pate's drawings, because I think Berger added post-tensioning in number 11 for the transportation. But imagine if Berger didn't do that, and imagine if Denny Pate didn't post-tension 2 and 11 in the order he did. It would have failed when they load tested it, and it would have been a done deal. But because of that, just a couple of little things that could add up to show why the failure happened, but also show how it could have been caught by failure. By it failing still when they were load testing. And wow, the little things they missed. All right, what do you think of that? Yep, sliding is BS. I played along with the best I can. I get a prying effect because I don't see 11 elongating. There's no force to push. Well, at one point there's some, but that's way into the collapse. That it by default, the length of it. Oh, the hell is the length of this? What's the length of this? If this is collapse, oh yeah, because you can see the length of it clearly. That by default during a collapse, it can push 12 away. And I already talked about it in another video because the way it starts doing it, and that's why you get that beautiful J bar showing at the top, unhurt, unharmed, no deflection. Walkway failure to go. Mark called the sheriff now. Oh, Embry. Darn it. Yes, Mark. That's what that would give you the confidence. Denny Pate to have that much confidence. If you do all the calculations on it, that darn deck had all that, and the only found out part is the transverse post cables were lacking. But I also talk about what kind of kinetic, and I say kinetic, not potential kinetic energy was canceling out each other. What kind? You know, yes, their force is down. What's the redirect? It drove. I wouldn't assume any of that. They use computer program to assume it. I'd want to play around and build it, put that all like that, and then dead load it. Since you had the deck, I think if you were going to do this again, make the deck, post tension the deck fully, and put it water test it. Put damn dead loads on the damn thing, equivalent to what you expect plus some change. You said no deflection is going to happen. Now the problem with that is you're going to have to make it a point loads. So if this is where you plan on doing it, put some blocking here, all the way out to here, I guess, and point load it as you expect to see it, because this would have a different point load, right, than the RS. Point load all this shit and let the deck rot. Let's see what happens. But point load it one at a time to see where the deflection is. As you would be load calculating, you ultimately, I guess, would point load it and work your way all the way down, point loading it. But that's old school engineering. Nobody's doing that. Nobody's point loading shit. They're using extrapolation and computer programs. Yeah, that's why we're in deep trouble now with everything in the world. Nobody knows how to use a brain anymore. They still might have been elastic, Mark, but they were beyond, in other words, I'm sure you said that before. They could still been elastic, but here's the but part. So the elastic, they were about 70%, all of them, where they can go. So they can go up to 100, right? So maybe it made it to 80% before that collapse happened. We don't know what the total amount you needed in deflection at 10 before the whole bridge would come down. Mark, in other words, maybe you only needed 75%. They had these all at 70, right? At whatever it is. But with this redirect of these loads, all this entire length of the structure. So Mark, I'm not into it. Well, if you were to calculate all the loads, how much actually load is down here at 10? How much is 10 and how much redirect is coming there? Are all the loads, we have to do some deduction, maybe take this off and maybe take off this end here and then count everything because it wasn't clamped down. Count everything from here, the base, all the way to the base of here, but remove this. Call this the zero force load, if you will. No, hell with that. Remove it from maybe here because this is still, I'd say remove it. Well, I'm trying to figure out what this would be in balance at. Oh, this would be a counterforce also because it's a counterweight. Okay. All right, so remove only the canopy here. Remove this and remove only this. And since this was on shims, nope. So I would say all the load that was on this member here during failure, just on, as you see the seat of my pants, I would delete this and delete this and call all the loads transferred down here. Ultimately, coming once they detention 2 and 11. Once the detention 2 and 11, save this because I'm counting this in balance, even though it's like 2 and 3/8 inch out. I'm counting this sort of like in balance, just standing up and kind of like a counterweight even down there. So I might do some counterweight deductions. So I don't know how much of a counterweight it would be. I don't know what it weighs. But if I want to just play along and try to guesstimate, so remove the weight of all of this, as I just said a second ago then. And this acts as a counterweight. So remove that and now take all the weight from here. Well, maybe I can hold maybe this much. So somewhere about here to maybe here. And count all that load is going down here. So 950 tons, they said. And let's just knock off 25 tons because we can. So let's call it 900 tons and let's have a little fun. Let's lock off 800 tons. So I'm at 800,000 kips right here. Right? 800,000 kips? Did I just say 800 tons and then I said 800,000 kips? That's wrong, isn't it? 800,000. What is it? 950 tons? So it's 1,600 kips. Did I just do that right? Oh, I'm melting down. That's that crack. 1,600 kips. But for everybody, 1,600 kips at what, Mark? Mark, at what point? The center of the friggin' deck. A load point right here. 1,600 kips. And that, I talked about how you going to get 1,600 kips to transfer with those transverse cables that can hold, I think it was both of them surrounding this. I did a video on maybe 600 kips it could hold. But the guy from OSHA has it working its way all the way out to here. I'm like, it can't. We saw it fell here. How are we talking about it failing down here? This was a resulting failure from detensioning, and this is patient over here. This wasn't the initial cause. It was releasing and changing the load path. So we got about 1,600 kips sitting here. I wish we had a better video. And here's the thing about Denny Pate's engineering is so awesome. 1,600 kips, I'm saying, and it didn't fail in his diaphragm of this section here. It failed out here. So out here, and I don't know what to call that, guys. I don't know what you call that. Flexural. Well, no, I'm going with Mark saying, yeah, exceeding the it's a zone. Oh man, check this out. Watch my retraction on this. If this is so badass and this is where it failed, and I just said it was badass, and it failed out here, that means I can't really count that his transverse cables were an issue because he didn't punch through. It didn't fail right here. It failed outside that zone a little bit right here. So that puts me back to thinking shear again. Why didn't it? And those cables could not be elastic enough because it's 1,600 pounds across this point here. But that across that point there, I'm trying to visualize it. £1,600, 1,600 kips. I'm trying to visualize it. I see the transverse cables. The transverse cables actually work in the same path, so that's not going to help. These transverse cables would have to transfer the load across all the cables, all of these guys. And that's where I come back, 1,600, right? 1,600 kips. And we got some huge mega redundancy, don't we? Let's see something here. Damn, I can't believe I'm doing calculations I said I wouldn't do. Where it is, D1 through D6. If they were transferring a load equally, don't you see greater than 1,600 kips here? This is why Denny Pate so confident again. Here, I mean, I can tell you 2,000 kips. What's the whole load of the bridge? 2 million, 2,000 kips. And you can see why Denny Pate was so confident. Like, I'm not worried about it. It's got some cracks in it. I'm not worried about it. As long as my post-tensioning, my transverse deck cables, D through 6 don't fail, and he didn't see it, that's why you can say, I'm not worried about it. Can you guys see that? Why you would say that if you designed this? Yes, I talk about D1. I don't like how I describe transferring, but it nevertheless it failed where it failed. Mhm. I'm just trying. I'm gonna have to. It's gonna be another video. I'm working something in my head, trying to get these forces across and down to the pier. I mean, before failure, just adding and theoretical, with the no bridge failure, just putting 1,600 kips, putting 2,000 kips, whatever you want, right there at that joint. I'm trying to make it fail at that joint. You get a punch it. You guys see it punching, don't you? It's got a pulling down effect too, though. That's the thing. It's got a clamp, so you'd have to add back the clamp force pulling down in the canopy, which would then be pulling back down, making 12 a load bearing member again, pulling downwards, trying to compress. I think I did that a long time ago video talking about it coming back around a circle. That pulling down force has a pulling down a force in 12 again. It's a like the umbrella. I'd have to do a video. I'm done. What I want to do for you guys, I want to weld something up. I want to weld something up. Kai's going bald, EM, or just balding. Going? I thought I was already bald. The crack in the walkway. Look, if I could have hair back, I wouldn't want it back. You know how many, my bald head is a babe magnet. It's been a babe magnet forever. How many babes rub my head? They love it. Guys even want to rub my head. It's a babe magnet. Girl, I would not want hair back if you gave me a pill to put hair back. I'm like, nah. Because if you told me couldn't have my bald head again, I'd have to have hair or bald head. I'm like, no, no, no. I'll keep bald head. Babe magnet. The point of the cross-sectional stress distribution not being uniform was right. So think about long the trend. What I'm working on in my brain is you have a 175-foot cable. Can you load a 175-foot cable at 2,000 at 745 kips? At any point, can you put 2,000 kips on that cable and it hold up? The answer is no. Can you line up? Can I line up two of them and hold 2,000 kips? The answer is no. Can I do three of them? The answer is, ooh, maybe. The margin's close. It would probably say you're stressing them. You're about it's close. And then if I say, well, can I do four of them? You start saying, yeah, yeah, yeah. Now you can. You got 2,000 distributed over this much. You're like, yes, you can. But the point is, I have to distribute it equally over all of them. And the only way to distribute it equally over all of them are the transverse cables. The transverse cables is where the Achilles heel is. They are only at 157 kips, 162, whatever, 187 live end, dead end force, anchor set. They're at 162. So two of them straddling this thing. I got a little zone going on now. I'm only at 162. But Mark, I didn't want to, get too crazy and complicated with you in there. But since you're so badass, we're trying to learn. I'll now add this to you. Remember, I'm teaching everything I can, but not everything I know. So what I'm leaving out is that remember that the shear links and all that are inside that zone too. So when you look at there, you have to figure out how many of the transverse cables are also encompassed inside your shear links. That also will lock in a bigger zone with transverse cables. Unless you just discount all the shear links and then you're now back to single zones of just two. So you would have to come here, Mark, and it still comes to the same difference. That's why I didn't want to bother you with it. I don't want to send you down an engineering nightmare. So you would now say that maybe that you do the math, you grab the drawings and you say, where are the drawings now? We are in the drawings, aren't we? So here's 162, and that's about 70%. So then, Mark, you would look at the 9, 10. Where are you? And you would try to figure out between wherever 9 and 10 is, you try to figure out how many transverse cables cross in that section, and then go, well, maybe I'll count all of these together. So maybe you count 3 of them together, Mark. You're only at 900, 162 times 3. I was way off. You're at less than 600 kips. Less than 6. Where you were looking, I can do better than that, can I? You're about 500 some change on kips. To try to transfer 2,000 kips across, transferring across all of these equally. I just don't see it. I see some deflection, some strain. And would it look like this, Mark? So here's the point load. Would it look like this, like that? See, not because I'm choosing a 45, but because I am. But would it look like that? Or would it be boxed shape? Or would the zone be rectangular shape? Well, Mark, what you do is you come to here and you see, well, how big is this? That's the shape. Then do a bird's eye view of it. However this is, I don't know what the as-bills look like. You do it a bird's eye view, superimpose it over here. Now I have the forces going down, and now try to visualize how it transfers over to here, your elongation. Then go to the outside, Mark, to complicate it for you. It's pulling in. It's trying to pull in. It's trying to push down, right? But these also are kind of pulling in too, aren't they? They're transverse cables. So they're kind of helping in the failure, aren't they? Because these guys are squeezing the deck inwards also. So what's the deduction for that? I don't friggin' know, man. I'm not a post-tension. I find the conflict in post-tension, transverse and the other direction. I find them canceling each other out. I have a little fun. I stick a needle through 2 rubber bands, okay? Through 2 rubber bands that cross each other. Pull one rubber band, you'll see the needle go the other direction. Pull the other rubber band, you'll see the needle will now go plumb. Look at that for a while and just start thinking about that. Then start making a grid of rubber bands crossing each other and sticking needles in them. And now have a little fun and start pushing down on the rubber bands. This is the crazy shit I do. And when you're done, you're on crack. You're on crack. You're like, no wonder I can't sleep. So I'm actually working on something, another concrete project, trying to come up with something for my man, Texas Barnuminium. You ever guys watch his videos? Trying to come up with something for the heat out there to using cables to cover his pads and get his non-cracking pad. Him and I talk frequently. He just used the Texas Barnuminium. You guys should watch him. I'm gonna do a YouTube video on commenting on using the roller tamper from Marshallton. It's pretty cool. I use a roller tamper, so he see me do it with him and I talked him into it. And there's the roller tamper. I gotta write him. I gotta do a video response, give him a little more thoughts about that to fine tune it. So what do we got here? This channel's just blowing right up. I just got to do something. I got to be crazy, I guess. The point of a cross section is, yeah, thanks, Mark. But I just wish I had more images to go over. Wish I had more images to go over. Where's my boy Embry? Embry took off on me. He said he was in it to the end. Well, is that what it was? Embry, woo! I'm in for the win. Oh, a little different. So, what can I say? Look, even if you give me a thumbs down, it still counts. Look, I gave a thumbs down. Nah, I can't do that. That's attacking myself. Thumbs down. Thumbs up. What? I just gave myself 2 thumbs down. Oh, that's messed up. Always a delay. It's all right though. It all counts as positive. Google doesn't interpret it one way or another. But hey, thanks for the thumbs up. So if I would do the thumbs down, it would still count as Google Thinking Interactive. I have no idea how to count this. I know they count comments active. That's why other people troll people when they say, "Hey, tell me what you think," or I like doing this, and they purposely say something that can trigger people. Man, that's you just bounce that guy's channel up on the list. They do that on purpose. I find that manipulative. If I ask a question, I'm just trying to engage for real. I'm not going to just ask a question and go walk away. These people ask questions and never answer it. Never respond to everybody. So they're just being jerks. Anyway, I got another concrete guy I'm going to troll soon on my other channel. The troll is and talk bad about him, putting down stamps. And I'm not sure at first to talk to him on the side first. If he blows me off, I'm going to attack him. He's going to be on one of my what not to do with concrete. So, anything else you guys want to say before I roll out? And we do know all the forces were on number 10-9 because that's the way the bridge came down. We see the points. Elongation got the brains turning. Yep. Elongation. Well, that's what's happened. Because if it did, you saw the amount of it in the drawing. If you were Denny Pate, would you be cocky enough? If you know your distribution, if you're sure that your distribution on any of the bridge weighing say 2 million pounds, and you are sure that you're like way over here, right? You're like this, and you swear in your mind you've determined that all the nodal areas, no matter what, is will transfer the loads onto all of the span, then you wouldn't care about cracks, right? You're just like whatever, it can all lay on the bridge, it doesn't matter. But this is where I see the problem is that the transverse cables. My guys, I talked to you about that. The transverse cables, I just don't get how they're only at 162. I don't get that. 162. I don't get that for any of the locations. 162. Spaced 2 foot apart. You know, or is it 2 foot apart? I don't get the yet it has load points. You know, it doesn't say certain parts of the deck increase the transverse. It's just 162. Basically, it's 162 all the way across. Let's say with North Landing, it's 160. That's the landing. The backspan, closures, everything's 162. I don't get this at all. Now I'll help you try to get it. So imagine I floor joist and I put out put 2x4s, 1x3 strips across every 2 feet, if every 2 inches, and you put your load on it. You see, you're not going to get any. FDOT did. They just said they're all theoretical. Period. They didn't say solid. They just said theoretical. Where's the damn bars? I'm gonna mess with your head just for a minute. Oh, I'll just say it. So the bars are way up there, right, in the hundreds of kips, 300 kips, 300,000 pounds. The nodal area was just reinforcement. It was just reinforcement. Yet it was point loaded at 8 inches. The 8-inch triangles I talked about a long time ago. They're point loaded at 300,000 kips. Or was it 300,000 on one end, 300 on the other, or 260? Whatever. I'm just showing you. Divide that in half. I'm going to do like what? No sound. Oh, you can hear me now? Oh, you can hear me now? That's weird. That's weird. I got some bills there. Anybody need them? Thanks. All right, so it says you're okay now. I can't wait to see this bill. I'm excited. Hold on. Yay! A bill. We changed in terms of your account. Let's see if they changed the amount they're giving me. I have no idea what this is. They've upped the late fees to $39. I don't have to worry about that. I don't have late fees. Thank you for telling me that. Okay. So much for that. There wasn't a bill. I'm disappointed. Hey, we're going to say anything else before I say bye-bye? We got anything else? Cognitive just popped in. You want to say anything else before I go? Right. Anything else before I take off on you? What kind of pipes were the cables in PVC? Oh, I'm glad Mark said that. Darn it, Mark, thanks. Not that question particularly, but I started doing this stuff here showing you how that post-tensioning after it was already failed, how that 200,000 kips could just blast away the bottom of this. That I started doing a little, my own 3D version of it, okay? You make your own. Trying to extrapolate from the cracks. The J-hook's in place, so I leave that like it is. The tension's in this direction. I know this is the crack from 4. I talked about that. All these other cracks, but you're reclamping at 300,000 kips, 260 kips, but there's a crack on the back side of this, so that negates any. You weren't going to get any strength out of it anyway, really. But on the face of it, there's cracks going like this from. Here's the deck, and here's okay. So here are. I want to take us out somewhere nice. You ready? I'm going in a couple minutes. Zoo. Huh? I said I'm talking to you. They can hear me.
I'm waiting for you to do the thing. We're going to finish the patty.
Oh shit.
I'm just patient.
Oops. I'd rather take you.
Reaching the point that I'm not.
I'd rather take you out. Okay. I'm doing a patio, and I'm doing multiple patios. She just called me out on it. Call me a procrastinator. Now could I argue that I'm not a procrastinator? I'm not a procrastinator, but I can start a project. How many of you guys got that skill set? I can start a project. I got some awesome skills on starting it. But here's a pipe, right? This hole right here. Here's the pipe. So I was sort of giving you wait a minute. The pipe's over here. I'm way off. So the pipe's over here, right? There's the pipe here on the outside of looking at the deck. Yeah, the pipes are here in line with the outside of 12. So here's outside of 12. This heavy red. Actually, the pipe's a little more inbound. Yep. Put that back straight. Grab it with the hand. Move it over. So here's our pipes, right? Look this helped you for, and here's that crack that we have gone through. And we know what it looks like now because we can see through it and see, you can see visually through it and see the bottom of this. You see the ass of that, right? You see that through here. You see it through here, but this pipe is left. My man just mentioned this pipe is left. It's the top of the deck, and with a little bit of routing out. So it looks like that. So when he had two, this is already cracked up. The day of Denny Pate saying put tension back on it. Imagine you put 200,000 pounds of force in here, 260,000 pounds of force. It's like a wedge. You're looking at the concrete right here, just sitting there, going in compression. But there is concrete here. Don't imagine, you can't get rid of this stuff in your mind. Just say I'm just pulling up and it's prying off. You know, you get a wedge nevertheless, but the clamping force is the wedge here. This stuff can start, giving way, not just clamping, closing up, and have an ability to act like a wedge and start kicking this over and start the process of failure, kicking this up, causing a new crack perhaps, causing these cracks to break more, even a buckling. But they balanced it. They said, I don't believe all that stuff. That's my thought about that pipe. What was your clarity? What was your question, your point? All right, Cognitive, I'll keep it up. I'll keep it up. But I'm going to delete the back end of it then because we got kind of funny longitudinal cables. Oh, we're talking about the longitudinal. I do not like the concentration of forces at the Victor. So yeah, he had what kind of pipes? They were usually pressure tested because they're going to get grout in them, and you get the grout in there through pressure and vacuum, and so they pressure test it. And it looks like your answer is this. It looks like damn good work, but remember this report says it's jackhammered later. And again, this is what I'm talking about, where it acts like a shim. The clamp force that's supplied is up here. It's above this pipe, but right here. So if I was to do that thing, I'm putting a 8-inch plate right here and applying clamp force here going up through here. And oddly, they don't show the photograph, but I'd be able to do it for you. I'll put a plate here and I'd start going up in this direction. You see where I'm not really clamping jack, am I? I'm sort of got this thing's already open. I'm sort of encouraging it to flip down, aren't I? The retensioning is sort of encouraging it to do what it did. Now, I'm not doing any fancy crap knowledge on that. I'm just using common sense on that one with you guys. That if it's already broken down the bottom and you reapply that, is it pulling back in or is it going to tip? Well, we know what ultimately happened, but we really don't have a good photograph, a video of it up tight. Bay of failure. So I'm getting something from my man here. Zooming out. Oh, so for clarity, I talked bad about this over here at one point, craftsmanship. I get to take that back now. This possibly was part of their shear friction resistance as per OSHA saying that they needed it. This is grinded, and I didn't like it, if you remember, but this would count against them as grinding, apparently, if OSHA's counting the shear friction across the base. So in one video, talking bad about FIU, maybe this was their intent. So an intent to follow that one rule. So I stand corrected and apologize. Here we are here. My man asked about the ductwork. Sealed up joints, and this is 175 feet, so I have no idea, 20 feet, 40 feet. You can measure through here, and I do have an idea. You can go through here and figure it out. This is what I'm talking about when I said that zone with you about, here, pretend like the transverse cables are here every 2 feet. You can figure out which one this one is, and you could figure out where the transverse cables would be laid, and you'd figure out how they would go through these shear links, if you will, these links. And then you could try to figure out the zone if you want. This appears to be on a mat that's not level. This reinforcement appears to be diagonal, this version of it. It does not appear to be, it appears to be diagonal. Could be optical illusion on my ass, but there's all a beautiful J bar and everything else. Acting like an anchor. Rods times 4, rods times 2. On this end, rods times 2. This is where if you can visualize, this is where the node goes on top of this. So this would be the deck, right? Going here. And then when they pour the node would then encompass the J hooks, the J bars. I mean, really, this is, so what I'm trying to say, earlier is that the bars had like 700 kips on them, the two of them, and no failure. Beautiful. Well, no failure, evident. All right. What else can I say? Any questions? Any questions? Well, Mark, they said grout was there. They say grout was there, man. So if I say grout wasn't there, that's because I'm only looking at images that don't show grout. So don't believe the images I see or talking about. You should believe the OSHA report, because OSHA is a bunch of outstanding. What am I doing? I don't want to go down that track. OSHA is good for workers, so I'm not. I don't want to. I'll slam NTSB, but I won't slam OSHA like that. They're good for workers. So I apologize for going down that track. I'm just saying he's accepting or made a declaration that of that. There's the beautiful J bars right here. There's the numbers. If you can figure out where these are before the collapse, they only gave us real images. We'd be able to tell so much about what these cracks represent here. The stop, the pushing that we were talking about, that they keep talking about, the pushing. That big piece of concrete on the ground, is that this? Well, I wouldn't think so unless it had that reversal and knocked it over first. Here's the beautifully cleaned off number B. Do you notice the amount of concrete on B? Do you really notice the amount of concrete on B? I don't see a bit of concrete here. Of course, this is images photography. This appears to be cleaned off also, and it's plastic. This, I mean, it's a beautiful, how the concrete popped off of this deal here. What's also beautiful is take note of the thread count on top of the end of this rod. It was so close to being outside the back of the deck that apparently they only put enough just to barely, here's the back of the thing, just enough to get that much concrete cover on top of the back of that nut. This one has a lot of depth. This one, since it's so close to that, what I showed earlier, it just has, there's the concrete. There's the concrete over this thing. Look at it with concrete on it. It looks white. It looks, encrusted. It looks encrusted with concrete. This does not look encrusted with concrete, does it? This sort of supports my statement that this was sort of just, not quite, everything wasn't copacetic in Denmark down at the bottom of there. I mean, this even has a sliding a little bit between this trumpet area, but it slid down even during the breakage. But this was seated here, I'm guessing. This J bar is in the bottom of 11 that everyone says slid and pushed off 12. This J bar, with all that ability to do all this sliding, is in perfect condition, beautiful condition. Don't get me wrong, this J bar you're looking at is in the bottom of 12, but in B section, not in one section. One zone, because one post-tension bar zone 1, I'm calling it, right, in number 11. Because number 1 is still buried. It's still encapsulating concrete, and there is no attack of that. So 23, what's up here? So this J bar is still in the concrete because we see the tip of the plate of number 1. This J bar we're looking at on top of there is here with this beautiful encapsulated concrete as I describe it. So those bars are here you're looking at. So magically 11 slid over, didn't shear these bars off, pushed this off, didn't bend the bar, and caused the failure of the bridge by sliding. So man, I talk about the amygdala file. Once you own a conclusive file, that you'll fight for it forever until you get new data. I don't know how many times I can keep entering this data and somebody not and still own that conclusive file they have. It makes me very so I'm being attacked. I have no choice but to attack back, and hence we're looking at my stupid ass video now. I mean, I'm being attacked by the idiots that still say it. Without grout, how is it? All right, we're back to the grout. That's what I was trying to figure out. So I'm going back to finding the grout. I see another shot. Here's a crack here, but we have plenty of, we see plenty of flexural action, dual action going here. Remember I said how you get that wrapping thing going on when I show in that one image, and I said that's because it had two crack, it had a rocking motion at some point. Well, here it is. There's one and there's two. And this second one goes up to here. And this is that one. That's not the diagram I was showing, but I'm showing you how we have a real world. You saw it crack, go rock back and forth, the end when during the failure. And this is how in real world those cracks present. So if you were only to show me this, I would be able to tell you, well, what happened was this took an action going left, up and down this case. It took, so I would have to find two actions, two movements to make this happen, an up and back movement. I could also probably theorize that this cracked only in this direction. And then when this hit the top of the pier, that then it resolved itself down here in this breakage here. So I would have to, but then I would then look for more data saying I need to know what force it would, I'd try to figure out what force it would take to cause us to break free, do that. And I would have to see an impact here or the dead lows of it, trying to act like a pair of two pencils trying to push apart, try to see if it's that capacity, a scissoring effect, if you will. Then I'd want to know how this spalled off, if that was the case. That's my nut job self for you guys. You show me a photograph with a crack and I go crazy. I go crack crazy. You know, you got regular crazy, I'm crack crazy. Oh man, I was doing a video on this guy. Oh, he's deadly crazy. This is an idiot. I'm going to do the idiot video on him. Look at this. He gets his own video. This guy got 400,000 subscribers. I just trolled him like unbelievable. I just didn't want to post it. I had 2 troll videos behind it. Yeah, so somehow we can look at this and I don't see grout, but magically there's grout inside this tube. That I look at this and I don't see grout here. I don't see grout here. I see a tube, but somehow the grout popped out of this tube and came this direction out and disappeared. And I don't see grout on the ground. I don't see grout here. I don't see it in the tube. But magically, and I just don't see grout. I couldn't find a receipt for grout. So, I mean, I see a ductwork here, but apparently grout is like a gold. And while they're demolitioning, of course, gold is taken separately. They vacuum out all the gold. And so this probably is why we don't see the gold right here or anywhere or appear, because it's gold. You know, grout is gold. Everybody knows that. Come on. So the grout gold has been removed per the Google Images. All the grout gold has been removed. Yeah. But you also do when you're removing grout gold, incidentally, never. Oh, I could do a video on this, couldn't I? That would be a good troll. Maybe that would go viral, and I get $10. I'm going to finish it with you guys. When you're removing grout gold, be careful never to open up your ductwork. And the reason why is, you know why? Because your gold might get into the wind. Grout gold is very light. Initially, it goes in heavy. You know, per pound. You know, it might be 150 pounds per foot. But once you apply grout gold, it expands, becomes lighter. And in fact, it's like helium. It will rise. So removing grout gold, when you be ready to capture it, you break open the ductwork, have your balloon ready, and it will blow up your balloon with all the grout gold out of its duct. Here, the grout gold will only go so far, but in this case, I'm sure the grout gold all went up in smoke. So grout gold is gone. Yeah, I don't find a grout. I don't find a grout gold. Yeah, Mark. But interesting, we do know the failure. We do know they separated. So how do we get them separating? I have to answer everything. That question is mine to answer, as far as I'm concerned, and it's something I keep working on. All I can think of is that when they post tension, that path was created with this tension, and this was already broken, that basically has to break apart, and the impact breaks it apart. Breaks it apart. And now concrete will break apart rebar pretty easily with impacts, with impact loads, but not, obviously not pushing. And so to see this J-bar in great shape, I would say it was an impact, a sudden breakage, a dramatic breakage, not pushing, obviously. If this is sliding over way up here, we would have a shear up here per their standards. Here's the deck. So right here, this J-bar should be sheared. They do have it sliding over, right? We know that. All these awesome engineers facetiously said, has this sliding over, and here's the J-bar. So this J-bar right about here, just only a matter of, I don't know, 2 feet, 3 feet, if you want to have fun, should be sheared or bent. Sheared or bent. As we look at the images that you can clearly find online, including the one I have. Including the one I have. I have no idea what that is. Not yet. Of course I do. I just don't recall. So Denny Pate should have played. Don't play the victim, the circumstances you created. Also did the thumbnail. He should have played this one. The trick is to play. The being smart is knowing when to play dumb. Denny Pate should have played dumb on the report. Because once you said he's got it wrong, you now know how it failed, buddy. You need to tell us how you could have caught that beforehand now. I just did a video only, a day before it was released, talking about they're never going to be able to tell, none of the engineers are going to be able to tell what happened. And his dumb ass fights the report. He should have left it alone. He should have known how to play dumb. I just did that video. I'm like, wow, this guy dropped the ball. What's up, babe? Yeah, we're out of here. I want to show him this thumbnail. So that J-bar was sheared, apparently, part of the crazy sliding people's thing, right about there. So you can find out where the sliding took place. If you figure out the length of the J-bar that we're looking at here, and we know it's hanging up, right? It's hanging up in one of these damn images. We got a different angle of it hanging up. Do we have that with, don't we have that with this guy? So you can figure where their shear plane, their sliding plane is, and you should see a bending moment in the rebar because they have it sliding. Ba la la ba la 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 la. And I'm not saying it didn't slide some degree at one point. It clearly has no point, no choice, but at that point they have it sliding. La 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 la. La 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 la. Ah, pixelating. You guys find another image. Count the end of that J-bar, which is way up here. Go to this drawing, scale it to this cross section here. Come back. There's your sliding that everyone's claimed that took place, right about where the damn arrow shows. So we're only talking just a crumb. I don't know, scale-wise, that might be 1.5 feet, 1.678 inches to be exact. Of course, I don't know 1.678 inches, but it was nice to say that. So we would go. That could be another video on its own, or somebody else can present that before me. I'm okay with that. What the hell? So you would come down from that J-bar, 1.675 feet, and you'd want to see this action where it crinked and bent all up. These rebar speak some volumes too. You can see the blowout of that, the buckling. We can't see it because they don't show it to us, but this is the buckle point here, where it's all blasted out. Also, this is where they had some stirrups. We can see where it didn't experience a buckling or whatever. The stirrups, right here, look, these stirrups. There's no breaking of the stirrups, but I think right about here, this looks like full development, full pieces. Well, of course, it sheared through it. This tells you at one point, this guy took a redirect and where it buckled. Right about here is where it didn't move. By then, it's already cleared. Man, if I had pictures here, I'd be able to give us another story. I don't want to give you guys my theoretical one right then. I might get owned on it. I mean, you guys might try to own that. I mean, own it as in not let me come back, retract, not knowing when I'm giving theory or not. So back here again. So there's a sliding right deck. There's a J bar only to there. We're only about 1.67999 feet. Going back to this one. From there to there, 1.6799 feet. It should be a bend. Well, it happens to be leaning against this. What are the odds of that? Maybe I got to change that to 7.2 feet. So this is their sliding point. J bar is okay, and this is their sliding point. J bar should have been anchored. At the sliding point, you'd get a big ass kink there. But right about here is the buckling point of the whole failure. I can't show it, but right here we have this redirect, multiple changes of directions. Awesome. Multiple things going on. Don't have data. And back to your comments, and we done. He wasn't playing dumb. He wasn't playing. Right. He should have played dumb though. That OSHA report came out. He should have said, "Wow, is that what they came up with? Huh? I just, he should have said nothing actually. Just play dumb." OSHA made their statement. They're the government. Are they going to retract it? No. Maybe they will. They should retract it. By the time he tells them exactly what happened. And when he does that, everybody's going to know. Going to know that he should have figured it out. He's going to admit to negligence. He's going to be admitting that he should have figured it out then too. So, but then the court cases will be over with, and that'd be it. But here's the thing, guys. You guys get a lawyer. We can get a class action lawsuit. Didn't they use federal money? Aren't we the public? So don't we have a right under public to be part of a class action lawsuit? Aren't we victims also? Didn't our tax dollars as payers of the United States go towards this structure? Aren't we entitled to use that structure? So therefore, can't we get a class action lawsuit? Any lawyer listen to this, you can put me down as your first client. That way I get the $20 you're gonna find. Everybody else gets the 20 rather. I get the 2 million or whatever it is, multi-millions. Don't ask what was the load on 17 feet of canopy. Oh, I don't know. It's changing, right? What's good to know though is you could calculate the buckling of that number 11. If you can take down that whole tire number 11, you can come up with the buckling, the force that it took to create that whole shape. Literally, you could recreate it with just redoing the base end. You could literally recreate it. That wouldn't cost $1 billion. That would just cost what it costs. And they would just apply the force from the top. And at any point that the buckling happened at the top, they'd have to retrain, basically clamping the top of the column and creating that same exact shape. And it's so easy to create, not easy, it would be difficult, but it would be so easy to do, because you would even see that some wire, some rebar is bent tighter and closer than the other. So you would be able to even figure out the path. You'd be able to duplicate this 100% and calculate the loads during the entire failure of number 11 if you wanted to. Then you could say, well, wow, does that have enough force to push off 12? But what's the point? They don't care about that. They're just, they're moving on. It's like auto accident. They're playing, they're moving on. We don't care about us. They don't care about us. That's a song. That's Michael Jackson. That's Michael Jackson. I just remembered that. Hey, look, I gotta go. I gotta play husband, play girlfriend, play boyfriend, whatever I gotta do today. Wear the dress. I'm on a YouTube live. Am I wearing the dress now? Oh, she doesn't like my games.
It is like 4 hours now.
Okay, I gotta go. She told me it's 4 hours. All right, so much for the joke. You know how to get all serious. Bye, guys. Love you. Darn it. So you didn't get to play around with. You didn't get to hear me troll myself. All right, take care. Damn, that's 4 hours. I'm in trouble. I'm in trouble.
It's already dark.
Is it trouble? It is already dark.
It's getting up.
Bye. Bye, guys. I gotta go. Psst, I gotta go.